So good afternoon, everybody, and welcome to this last session of the conference on front-end electronics, trigger, data acquisition, and data management. We have 7 talks in this session, which, by the way, will be chaired by Martin Grossman from PIsa and by myself. I'm Ludovico Ratti from Università di Pavia and INFN. As I was saying, we have 7 talks, 4 in the first part and 3 in the second part after the coffee break. In the first part, we will also have, at the end, the poster review. We also have 56 posters in the other room, so if you want, every now and then, you can go and have a look at them. I think we can start with the first talk, which will be given by Serena Loporchio from INFN Bari. She will talk about silicon photomultiplier multi-channel ASIC for high-resolution Cherenkov telescopes developed for the PSCT camera. Okay, so.
Prova. Si sente? Okay. Good evening, everyone. My name is Serena Loporchio from INFN Bari, and today I will discuss about the development of a silicon photomultiplier multi-channel ASIC, which was developed for the camera of the prototype Schematic telescope. So let's introduce PSCT. Like I said, a dual mirror design with the camera in the focal plane of the second mirror. And this particular design allows for the magnification of images and compensation of optical aberration, allowing for a very compact and high-resolution camera, which will have more than 11,000 pixels. Each one of them will be a 6x6 millimeter squared silicon photomultiplier for a total field of view of 8 degrees. The camera will be less than 1 meter in diameter. Currently, there is a prototype of this telescope, which is being developed at Whipple Observatory in Arizona. And up to today, this prototype is only equipped with less than 2,000 pixels. Part of them are Hamamatsu silicon photomultipliers. Part of them are Fpgas silicon photomultipliers. And the current front-end electronic is based on a discrete preamplifier, followed by the Target 7 ASIC for sampling, digitization, and the trigger generation. An upgrade of the camera is foreseen in the upcoming future, and this will include the equipment of the full camera for a total of more than 11,000 pixels, and each one of these pixels will be Fpgas NUV HD silicon photomultipliers. And the front-end electronics will also be upgraded, and it will include the smart preamplifier and the Target C and T5T for the sampling, digitization, and trigger generation. The SMART is which stands for a CPM multi-channel ASIC for high-resolution Cherenkov telescopes, has been developed by the Francesco Licciulli and Giuseppe De Roberti with the support of the electronic CAD of INFN Bari. And it is a preamplifier which is optimized for photon counting. This preamplifier has 16 input channels with a transimpedance amplifier, and each of these channels can be adjusted using a 20-bit global adjustment to fine-tune the gain, the bandwidth, and the pole zero network of each one of these 16 channels. Additionally, we also have a 8-bit Daq, which will be used to fine-tune the bias of each pixel in the camera. And in the end, we also have a slow monitoring of the silicon photomultiplier current using a 10-bit ADC. This is the architecture of a single channel, and as we can see, there is the transimpedance amplifier for which we can adjust the gain and the bandwidth along with the bias of the single pixel. And after that, we have two paths. One is what we call the fast path, which has a tail suppression filter, which again can be adjusted channel by channel, and what we call the slow path, which has an additional gain stage, and it is used to measure the current of the silicon photomultipliers. We can also, like I said, change the Daq bias voltage using a Daq to fine-tune the bias of the overvoltage of each silicon photomultipliers. Since in the camera, every silicon photomultiplier will have its own breakdown voltage, we can use this Daq to fine-tune the voltage that is given to each channel in order to equalize all the overvoltages. As we can see here, we have a linear trend of the bias of each silicon photomultipliers with the Daq counts. And we have seen that this Daq goes from 0.75 to 1.9 volts. So the range is approximately 1.2 volts. So we can fine-tune the bias of each silicon photomultipliers with approximately 47 millivolts per Daq. So we performed a full characterization of this ASIC, coupling it with an array of silicon photomultipliers, like we can see here in the picture, where we have an array of 16 silicon photomultipliers, which was developed for the PSCT camera. And we performed these measurements by fine-tuning 3 parameters, the gain resistance, the filtering capacitance, and the pole zero network for pole zero cancellation. And we measured for each configuration the gain, the signal-to-noise ratio, and the shape of the pulse as a function of these configuration bits. The setup was placed inside a dark box in order to exclude any source of interference from external light sources, and we illuminated the CPM arrays using a laser, which was placed, after which we placed a diffusing lens in order to illuminate uniformly all the pixels. But also, in order to reduce the crosstalk contribution, we performed measurement with a mask in order to cover the pixel that we were not observing. And we repeated measurement using an external pole zero with fixed discrete components in order to match the signal of the silicon photomultiplier with the internal pole zero cancellation network. We set the configuration bits through a PC interface with the smart, and we acquired waveforms with an oscilloscope. Here we can see the results of this characterization, and we have here on the left the charge distribution with a very good signal-to-noise ratio, which is about 5, both for the charge distribution and for the amplitude distribution, which also shows a gain of 2.4 millivolts per each photoelectron. And from this distribution, we selected only the waveforms corresponding to a single photoelectrons, and we averaged them, which is reported here, the average waveform, and we fitted the average waveform with a Gaussian on the peak and an exponential function on the tail in order to estimate the width of the pulse, which for this configuration is about 12 nanoseconds, and the recovery time, which is here almost 6 nanoseconds. We also performed a scan of the dynamic range, and here we can see the comparison for different configuration with and without the external pole zero, which, as we can see, reduces the dynamic range from about 900 millivolts to 600 millivolts. Here we can see a summary of this measurement, where we can see the dependence of the gain from the filtering capacitance and the gain resistance. As you can see, the gain mainly depends on these 2 parameters, and it is decreasing with increasing R and C. We also performed a scan for the full width half maximum, which is reported here. And as we can see, it mainly depends on the filtering capacitance and the pole zero network. So among all the different configurations that we can achieve with the smart ASIC, we have that the gain can be tuned between 0.57 and 3.27 millivolts per photoelectron, while the width of the signal goes from 7.68 to 19.16 nanoseconds, and the recovery time goes from 3 to 19.58 nanoseconds. We also coupled the silicon photomultipliers and the ASIC to the front-end electronic modules that will be used inside for the PIsa camera. So we used this time not one array of silicon photomultipliers, but 4, in order to have 64 channels, since the front-end electronics can digitize up to 64 pixels. So we used 4 silicon photomultipliers arrays coupled to 4 smart ASICs, and we again placed the setup inside a dark box, and we used a PC interface, which was to control the smart and the front-end electronics to set the parameters and the Daq, and to acquire data. We acquired data for about 10 seconds, so this means that we acquired about 10,000 waveforms. And here is a sample of these waveforms with the corresponding charge distribution integrated over an integration time of 10 nanoseconds. The signal-to-noise ratio of this distribution is good. It's not as good as the one that I showed you before, but this is due to the introduction of additional noise from the front-end electronics. We also tested the trigger capability of the module, because the module can generate its own trigger by using a trigger group of 4 neighboring pixels. So in each trigger pixel, we have 4 silicon photomultipliers. And by using the smart registers, we can disable or enable some of them. So we did a threshold, a scan in the threshold, which is adjustable for each individual trigger pixel. And as we can see here, we disabled 3 to 1, we enabled 3 to 1 pixel. So we were basically triggering on 3, 2, or 1 pixel of the whole trigger pixel. And we looked for single photoelectron plateaus, like we can see here, from which we can determine for each pixel in the trigger group the corresponding Daq count threshold for each photoelectron. As we can see here, we have that the threshold in Daq values decreases with the plateau IDs, of course, and it has a linear trend, which is reported here, and goes from about 140 to 170 Daq per photoelectrons among the tested pixels. And here on the right, we have the rates, which we can see that are grouped according to the number of enabled or disabled pixels. We then proceed with the production of almost 750 ASICs, which will be used for the PIsa camera. So we performed quality control tests on these smarts. We implemented a test chain in order to test the main features of these ASICs and check their basic functionalities, such as the slow monitoring of the current of each silicon photomultipliers, the response of the ASIC to a laser pulse, and the variation of the pulse shape with the smart configuration parameter, the ones that I was talking about before, R, C, and the pole 0. And also, we looked for the variation of the amplitude with the Daq for the silicon photomultiplier bias fine-tuning. The setup was again placed in a dark box, but this time, since we were not interested in the single photoelectron resolution, we used a higher intensity laser, and again, we used the PC interface with the smart and front-end electronics to set the parameters and acquire data. If you have more curiosity about these quality control measurements, I strongly suggest you to go and check Giovanni's poster during this poster session. It will show you some nice results that we got during this test campaign. So here I only show you a summary of what we did during each run. So we did this loop on the different configurations that we can achieve by tuning the parameters of the smart. And here we report for the 64 channels in the module, the mean amplitude of each pixel, along with the full width at half maximum, and the tau the distribution of the tau, the recovery time of each pulse. And we can see that here we placed some hedges value in order to determine if the ASIC was properly working. Here we show you the loop on the Daq values, and as we can see here, for only 16 pixels, we show that the amplitude decreases while increasing the Daq value. This is something, of course, that we expected, since higher Daq values means lower overvoltage, and lower overvoltage means lower gain. And we fitted each of these curves with a linear function, and the slope of these functions of these curves are reported here, distributed almost uniformly according around mean value. We then proceed with flat fielding measurements of the module. So like I said before, what we did was that we report scattered, and they are not the same also here in this distribution. We go from about 27 up to 40 arbitrary units for the gain, but we are interested in having a uniform gain for the module and then for the camera. So we repeated this procedure for all the pixels and for different Daq values, as we can see here, and we report here all the 64 pixels. The problem is that, as you can see, there is no Daq value that can achieve the same gain for all the pixels. This is due to a large spread of the gain of the single pixels with the overvoltage. So what we can do, what we are thinking of doing, is that we were planning on using a reasonable gain with the corresponding Daq for all the pixels that we can achieve, for all the pixels that can be tuned with this Daq value, and use the closest Daq value for those that are outside of this range. So to sum up my presentation, we showed you the performance of the smart ASICs when coupled with silicon photomultipliers from Fpgas, and we showed you how the signal and the shape of the signal and the gain depend on the parameters R, C, and pole 0 to fine-tune the gain and the shape. And we also showed you the results of the quality control performed on the 750 ASICs produced for the camera. Out of these 750, only 7 ASICs were found to be defective, so we are less than 1%. And up to now, we are doing studies on the gain versus the Daq value. So we are trying to understand what kind of dependence is there. And a new design of the smart ASIC is ready to be tested, and the studies are ongoing for future upgrades of this ASIC. My presentation is over. I thank you very much for your attention.
Thank you very much for your very comprehensive presentation. Are there any questions from the audience?
You didn't show the bandwidth of your preamplifier and how the 3 dB bandwidth goes with gain, because you only showed signal width. Do you know what the bandwidth is of your preamplifier?
I actually don't remember.
Okay.
I'm truly sorry.
Okay. Thank you.
Other questions? I have one, actually. I don't know if you, I don't remember you mentioned the process that was used for the design of the ASIC. I mean, the technology.
Yeah, it was done, but no, sorry, I didn't get your question.
I mean, was it CMOS technology? Or
Oh, yeah, it should be CMOS, but I'm not 100% sure.
The node.
Yeah,
Okay.
I didn't take part in the design of the ASIC.
That's okay. Thanks. Okay, if there are no other questions, let's thank the speaker again.
Thank you.
And the next speaker is Dinyan Rabadi, okay, from CERN. He will talk about the a scouting system for the level 1 trigger for the phase 2 CMS upgrade.
Can you hear me? Very good. Okay. Yeah, my name is Daniel. Okay. Like this? Ah, perfect. Okay. My name is Daniel Badi. I work at CERN, and I'm going to talk about the 14 megahertz level 1 trigger scouting system that we want to deploy through the CMS phase 2 upgrade. Very briefly, CMS is undergoing a big upgrade for the High-Lumi LHC. From the trigger side, this means we'll get new trigger primitives from the muon system and from the from the calorimeters. And for the first time ever, we'll have trigger primitives also from the tracker. So we'll have tracker tracks at the hardware trigger. Of course, we're going to do a big upgrade of the level 1 trigger itself as well that I'm going to briefly introduce. Decision, all of the detectors read out and sent to the high-level trigger, which runs in a computing farm. From the high-level trigger, we do further reconstruction and then store it on tape or permanently. In phase 1 and phase 0, which will go until 2025, we're expecting a peak pileup rate of up to 60. We then read the detector at 100 kilohertz, so this is the level 1 readout rate, and then we store physics events on tape at about 2 kilohertz. In phase 2, which starts in 2029, we expect a peak pileup up to 200. Accordingly, the level 1 trigger rate is going to be increased significantly to 750 kilohertz, and also the HLT trigger rate will increase to 7.5 kilohertz. Okay, how to deal with these, this massive pileup, this 200 pileup? The first thing we did, we needed to increase the trigger latency. We needed more time to do more advanced calculations. We're going to do vertex finding at level 1. Displaced muons will be available. We're going to do particle flow in FPGAs. On the menu side, the global trigger will undergo an evolution. At least we'll have topological trigger algorithms at higher resolutions. This means invariant and transverse masses. The bunch crossing window, so the window of events that we can look at the same time will be increased to 3 bunch crossings. And of course, there will be machine learning algorithms up and down the chain from reconstruction, particle ID to the menu itself. On the left-hand side, I have a diagram of the level 1 trigger, how it should be. The important each of these boxes is its own system. The important thing here to take away is that we have a local reconstruction layer with, for instance, the track finder, the track finders, muon track finders for various regions of the detector and a regional calorimeter trigger. And then we have a global layer that reconstructs, that is responsible for certain particle types, as well as a correlator trigger that, for instance, does particle flow. And then we have the menu layer, which is implemented in the global trigger. So it progresses down the chain. Okay. So what is data scouting, the topic we're going to talk about today? This is the idea here is that we analyze partial events, so either only a subset of detectors or the data at limited resolution at a much higher rate than we could otherwise do given the trigger budget or the time constraints we have on the trigger. This could enable the study of exotic signatures that wouldn't otherwise fit in the trigger budget, again, either for time reasons or for bandwidth reasons, because we just can't read out the detector. So CMS has been doing this at the HLT level, at the high-level trigger level, for quite a while already. Here we save reconstructed objects, so objects that HLT reconstructed for certain topologies at a much higher rate than we usually take physics data. I mentioned already in phase 1 we store data at about 2 kilohertz, but we have, for instance, here these tiny events for digets that we read out at 5 kilohertz, just these digets, so much higher rate than usual. And I put some of the papers that came out as a result of this HLT scouting out. A crucial thing here is that the HLT scouting is limited by the bandwidth of the level 1 trigger. Everything one throws out at the first layer, of course, can't be used anymore at the HLT. So for phase 2, what we want to do is we want to grab the reconstructed objects of the level 1 trigger, these good trigger primitives that I mentioned already with the high resolution. Those we want to take and pipe into a big computing farm and do further processing, either do a semi-real-time analysis or store tiny event records that can later be analyzed. As I mentioned, this is planned for phase 2. However, we are demonstrating this already now with a small-scale demonstrator using the current level 1 trigger. So why is this? Why can this be useful? It's likely to be useful if we're looking at a process that is rare, of course, but also difficult to trigger at the level 1 trigger level. So, for instance, if it looks basically like background, but it still needs to be sufficient. We need to be able to study it given the resolution at the level 1 trigger level. There is a way around that second point. We think we can scout for a potential new signal if it is hard or impossible to analyze at level 1. And if we see something interesting, then we can reconfigure the trigger and point its full might at it and analyze this event offline. So some channels that could be useful have been identified, and I've put a subset of these here. This goes from dark photons to classic B physics, but also is maybe a bit more exciting right now. W23Pi would be a good candidate because essentially it's impossible to trigger on. Okay, further to physics triggering physics analysis, this scouting system would also be incredibly useful in monitoring. One could imagine an extremely high statistics data quality monitoring system based on scouting, where we have where we can look at the pre and post firing of the trigger without special configurations. We can create real-time heat maps to quickly spot problematic channels. We can do cross-checks between data and emulators. And very usefully, this is unaffected by issues in the readout system. Currently, for instance, we do have the problem that, for instance, we are blocked by a hot channel and can't take data, which makes it then also difficult to spot the actual hot channel. With such a scouting system, this would be trivial. Further to that, we're looking at per bunch luminosity measurements with, again, very high statistics. This being investigated for muons at the moment, but could also be done with physics channels with high statistics, for instance, Z decays. Okay, what do we need to make such a scouting system work? I've put here, again, the diagram of the level 1 trigger, and next to it, in parallel, the scouting system. The idea is to take trigger data, capture it using the spare outputs of the level 1 trigger. We'll use the same links and protocol as the interconnects of the trigger itself. These data go into FPGA boards that do some local pre-processing and zero suppression, and then transfer the data to I/O nodes via TCP/IP. The I/O nodes would then be equipped with, so those are normal computers equipped with GPUs or other processors, run some distributed algorithms that extract features that we think would be interesting, and if we find something interesting, then we send this via an interconnect to a stream processing farm that that eventually stores these data into a feature DB that will enable us to do analysis by query, and eventually then the analysis results, or as I mentioned, tiny events are stored on tape or permanent or other permanent storage. All right, this is a fairly complex system, so we've designed the architecture to be scalable, and in the baseline proposal, the idea is to take just the data that the global trigger already receives, as well as the outputs of the global trigger. In a further stage, one could take the local reconstruction results, as well as potentially even the trigger primitives, which is, of course, a lot of data. We've identified a candidate for the scouting readout board. This is planned to be the Daq 800 hardware platform. It is currently being designed as the CMS readout board. It hosts two powerful VU35P FPGAs from Xilinx, has about 1.2 gigabit per second total input and 1 gigabit per second output. On the firmware side, we're going to profit from developments done by the Daq group for this readout board. Namely, we are going to use an almost unchanged TCP/IP sender in firmware. This has already been demonstrated for the current Daq system, so we're fairly confident it works, of course, with lower bandwidth and so on, but the principle is sound. On the receiver and pre-processing side, of course, we'll need a scouting-specific solution. As I mentioned, the input rate is about, the input bandwidth is about 20% higher than the output bandwidth, so we'll need some moderate zero suppression. On the distributed computing side, there's been some work by colleagues from the that are doing DT scouting. I've put here the paper that has recently been published. They use Kubernetes as an orchestrator with Kafka and then Dask doing the processing. Of course, the industry here is rapidly changing, so we're keeping an eye on it. This is currently our target for the Run 3 demonstrator to be used. We'll see how that goes. So I mentioned already the demonstrator. Here is the architecture of this. This here is the current phase 1 trigger. It's in structure quite similar to what I showed for phase 2. We send the data from the global muon trigger, the barrel muon track finder, the global trigger, and the calorimeter trigger. All of those should go into scouting boards, and from there to what is the equivalent of the I/O nodes that I mentioned, and then we have permanent storage here. For the moment, since 2018, we've implemented the links from the micro GMT to scouting boards, and since about a year, we've implemented the links from the calorimeter trigger to another scouting board. The barometer track finder and the global trigger are about to be commissioned. The scouting boards we use here for the Run 3 demonstrator, we've got two. One is the VCU128 dev kit by Xilinx. The nice thing here is that it has approximately the connectivity of half a Daq 800 board and a VU37P FPGA. So this is not quite the VU35 that the Daq 800 is equipped with, but it's sufficiently similar that we think that it's still a useful prototyping board. We will be transferring the data via TCP/IP as for phase 2, but currently we've demonstrated only with DMA. The second board we use is the Micron SB852. This is interesting because it has machine learning inference capabilities with a special framework by Micron. So we're going to use it on problems that seem where machine learning is going to be seems to be useful. Here, data needs to be transferred by DMA to the host computer because of limited optical bandwidth. Okay, some examples of what we've done with this demonstrator system. At the end of 2018, we were already taking muon data, and this was taken during a so-called emittance scan. Here, the LHC moves the beams either in X or Y axis towards each other, which of course modulates the luminosity. The scouting system was recording all output muons by the microglobal muon trigger, and we could see that the number of muons were proportional to luminosity. This is this plot here, and then what one also sees, it's nicely corresponds to another other luminometers of the CMS collaboration. So this was a nice result. Last year, we were taking cosmic muon data with no magnetic field on. So we showed here the relationship between the impact parameter, so the distance of the muon track from the beamline, and the phi coordinates of the incoming and outgoing muon. The idea here is that CMS sees cosmic muon twice. It sees it once in the top part of the detector, and then 50 nanoseconds later in the bottom part of the detector, because the detector is fairly big. So the idea here is that the relationship, the impact parameter is related by the cosine of the difference between the angles halved. We see this relationship nicely confirmed. Okay, and on my last slide, I show first results with beams. Here we took data, again muon data. The idea is the beam was fairly dirty, so we had a big cloud around it that was passing through the detector. It was during the beam test of the LHC in October. We first saw muons passing through the negative end cap and 2 bunch crossings. So again, 50 nanoseconds later, we saw the same muons passing through the positive end cap. We're fairly, we convinced ourselves that these are indeed the same muons by making the difference in X and Y coordinates, and we see this is nicely centered at the 0 coordinate. One thing to point out with these plots and also the previous plots is that this is a nice example of scouting because CMS itself can't be read out multiple times, can't be read out in subsequent bunch crossings. We just don't have the bandwidth. The detector front ends wouldn't work. So this is something that is essentially only possible with scouting. And the very last plot I'd like to show is from the commissioning of the calorimeter scouting. Here's just an occupancy plot of E gammas, so electron and photons that were seen, that were transmitted by the calorimeter trigger to the scouting system. As I said, commissioning is still in progress. So we're working towards a full system there. And then I have a conclusion slide that I won't go through given the time. Okay, thank you.
Thank you very much for your nice presentation. The paper is now open for questions.
Maybe I could be a little bit provocative. The trigger system in CMS is already quite complex. And in fact, when the calorimeter trigger was upgraded a few years ago, it was included some features which would allow you to investigate future triggers, which as far as I know, has not really been exploited. I mean, the system you're describing sounds quite complex on top of an existing system. And for your demonstrator in run 3, you're not going to be able to use things that will be available later, such as tracking data. Why is it important to have this extra hardware to investigate certainly difficult triggers, but why can that not be done offline, as it were, and then incorporated into the regular trigger system if physics events of that kind are particularly interesting?
So I think the target for us is, for instance, the W23 pi is, this is just impossible. Like, you can't do it offline. You'd be looking at 0 bias for the, like, forever, because, I mean, 3 pions not going to trigger on that. Right, so we're looking at problems that are really essentially impossible to trigger on. That's where we see scouting to be useful.
But in some sense, what's the difference between scouting and, for those kind of events, just minimum bias triggers, a sample of minimum bias triggers?
The statistics. We can just take all of it. In scouting, we take, every collision. So, I mean, 40 megahertz is not quite true because of the orbit gap, but yeah, we take it at the bunch crossing frequency.
Other questions?
One thing I didn't completely understand, you do the scouting on a subset of data, and then if you find something interesting, you don't have access to the full data for this event because that's gone already. So the only thing you can do is learn from that and change the trigger in the future to be sensitive to this. Is that correct?
This is one of, so essentially either you have everything you need for the analysis already. So for instance, if, I don't know, if your trigger objects are sufficiently well reconstructed that you can do a useful analysis on it, then you're fine, of course. Okay. But otherwise, yes, as you say, we would try to spot something interesting and then point the trigger at it. Yes.
Okay. Thank you.
Other questions? So, no other questions? Let's thank the speaker again.
Thank you.
The next speaker is Giuseppe Tartarelli from INFN Milan. He will talk about the challenges on electronic systems in Atlas entering the new, the high luminosity era.
So, can you hear me? Yeah. Okay. So, so as you might have heard earlier this week, Atlas is doing a large upgrade program to cope with the operational condition at the high Lumi LHC, and in particular to the increase of pile-up, which will be about 200 events, so five times higher than today. Part of the upgrades have already been done for the current data taking, which is the one which is starting now, especially for the calorimeter trigger and for the muon chambers. And then there are new upgrades that are being doing now. And this is a completely new inner tracker and the new end cap timing layers and additional muon chambers that will be installed. And in addition of this, there are significant changes in the existing front end of detector and the trigger electronics, which are foreseen for all the other systems. So why changing the electronics? There are various reasons. One aim to maintain or improve the existing performance in terms of acceptance, efficiency, resolution, despite the new condition. Then some existing components have limited radiation tolerance and would not withstand the additional expected dosing. Some components are very old now, they are obsolete, so are very difficult to maintain and repair. Then, based on the experience gained in the past runs, one wants to increase the redundancy, ease the installation, removal, and reduce the single points of failure. And finally, the trigger will be upgraded to handle the new expected pile-up levels while trying to keep the threshold at today's level. And this will use the highest granularity information and resolution which is possible and which is coming from the detector. And the detector readout electronics that we have today is not compatible with this future scheme, and so it needs to be upgraded. And what is this trigger in phase 2? This will be a single level hardware-based trigger in which data flow comes from tile, LAR, calorimeters, and muon system at the LHC bunch frequency. And this uses feature extractors here for calorimetry muons, which are then combined in a global trigger part here to identify physics objects and calculate event level physics quantities. The maximum output will be 1 megahertz with 10 microsecond latency. Then at the level 0 acceptance, there will be tracking in ITK in a region based on objects identified by level 0. And the event filter will be a heterogeneous commercial system with the CPU cores and possibly accelerators. And then the output will be about 10 kilohertz. The connection between the front-end serial links and then a DAQ commercial network here is done using these cards here, which are called Felix card. And these are custom-designed PCI Express I/O cards, which are hosted in commodity servers and that are designed to be as much as possible detector agnostic. They will route all the needed signals, so readout, configuration, trigger, clock, and so on. And the Felix that we will have in phase 2 is in an evolution of the Felix that we are using already now for the system that have been upgraded in the past year, so in phase 1. And we have already first prototypes available for Felix, level 0 muon, global trigger, and so on. So, as I said, so electronics of the calorimeters and the muon system is not compatible with this architecture, so this requires a complete replacement of both the front-end and detector system. The front-end electronics is located on detector and is subjected to radiation. This usually amplifies, shapes, digitizes signal coming from the detector, and ships the data of detectors. All of the on-detector buffer will be removed, and the full granularity data will be streamed off detector at 40 megahertz. Then the data is sent optically off detectors, and here we make a large use of the CERN GBT, low-power GBT, VTRX, which are radar. The off-detector electronics are fast preprocessor, Fpgas-based, that convert the raw data into calibrated information that feed the trigger system. And they will do data buffering awaiting the trigger decision. They are usually located in underground counting rooms, and so they are not exposed to radiation. And what are these radiation level that we expect? I have tried here to summarize a bit the total ionizing dose, the neutron fluencies, and the other influences. So the worst situation, of course, is in the tracker closer to the beam and for the pixel, where we have these doses here. And in fact, after half the lifetime of the experiment, the two innermost layers of the pixel will need to be replaced. The radiation is also pretty high in the timing layer, and again, they plan to replace the inner and middle rings after these doses here. Then the situation somehow is better as soon as we get out of the at higher radius, but we still have this value here that we have to cope with. And so radiation hard or radiation tolerant design are needed, and a lot of work for qualification for TID and single events effects, so single event upset, bit flips, latch-ups. And this includes all the ASICs design, the links, the DC-DC converters, the linear regulators, and so on. So now going a little bit system by system, in the liquid ion calorimeter, there will be no change to the detector, but a full replacement of the front end and of detector electronics. And here we need a new front-end board, which is based on two new ASICs. One is a preamper shaper that has two overlapping 14 bits gain to get to the desired dynamic range. It's followed by a shaper, and has been verified to have a low noise, good low nonlinearity, and also low crosstalk. This is all within specification, and also the radiation tests are okay. This is followed by an ADC, a 15 bits ADC, sampling and 40 megasample per second. And again, here we have verified low noise, low crosstalk, and the desired ENOB. This is the front-end board. We have a prototype that has demonstrated a full readout chain and also meets the analog specification. Then we also built a prototype calibration board with needs two additional ASICs. One is a pulsar with high-frequency switches, and the other is a custom 16-bit Daq that commends the high-frequency switches. Then the data is sent off detector, where there is this board, which is called the LASP, which will receive all the CaloCell data with optical fibers at 10 gigabits per second. And all this amount of data will be processed by FPGA-based board, which will do digital filtering, calculate energy, time, and transmit the data to trigger and the IQ. There is still some discussion here of which kind of FPGA to use, Stratix or a new Agilex series, and this will be decided balancing the resource and power requirements. This board needs two auxiliary boards. One is an interface to the DAQ system for monitoring and data transmission, and the other board handles the TTC signals, configuration, and monitoring. For what concerns the tile calorimeter, the situation is very similar. There will be basically no change to the detector, but there will be new front end of detector electronics will be housed in new mechanical structure which are called the mini drawers. Again, here the signal for the photomultipliers are amplified shaper with 2 gains to cover the 17 bits dynamic range. Then there are 2 12 bits ADC working again 20 megasample per second. And then there is this board here that synchronizes the data and sends the data of detector, where there is a processing board that controls and read out of the modules, propagates the TTC info, and does cell energy reconstruction and monitoring. A hybrid module has already been built with some of these components and will be kept inside the incoming run. For the rest, the pre-production of this board here and of the motherboard has been done, and also the mini drawer production is going on according to the schedule. The Muon system will complete the detector upgrade that has already been done in phase 1. There will be a new RPC with thinner gaps, so they will be operated at lower voltage, and so will be a smaller effective signal. New triplet layer of TGC, and the new small diameter drift tubes that will replace the existing drift tubes where the space is limited for the installation of the new RPC. And moreover, all the drift tubes electronics will need to be replaced because this time also the drift tube heads will be used in the trigger logic. The RPC electronics uses a silicon an amplifier done in silicon BJT, and then a new ASIC in silicon germanium, which includes a discriminator, TDC, and serializer, which sends the data to this board here that does trigger and readout, and these prototypes are already available. The drift tubes has an amplifier shaper discriminator, followed by a TDC, a chamber service module that organizes the data and sends the data of detectors. Again, here we have some pre-prototype of these components. Now, going into the new system, the ITK is a full silicon tracker with pixel plus strip. The pixel readout is done by this chip here, which is a successor of the RD53A chip. These are the size of the pixel matrix. This integrates a charge, generates in the pixel sensor, amplifies, digitizes the signals, and sends information to the IQ system. It has a differential front end, a low settable threshold, and 1 MHz readout. Triple modular redundancy has been implemented for critical parts. There have been an intense testing campaign in the last year of the chip. A few issues have been understood and addressed, and so soon the version 2 of this chip will be submitted. The silicon strips requires three chips. The first is called ABC Star, which is done in this technology and provides analog amplification, shaping, binary discrimination, buffer pipeline. And also again here there is a triple modular redundancy for the register, clocks, and reset. And then other 2 chips that you can see here, that one is an hybrid controller and the other one does analog monitoring and control temperature, voltage, and current. The ABC Star version 1 the production has started, and the pre-production lots under probing. The pre-production test of these other 2 chips are well advanced, and but they need to complete the radiation campaign. Then there is the timing layers. So these are two LGAD double-sided layers in the end cap. They will use LGAD sensor of this size here, and they need a resolution at this level. The electronics is this Altirock chip done in this technology. This is the size of the chip. It has a preamp, a time of arrival, and a time of threshold for each channel. The Altirock 2 also includes the data buffer and transmission part, which was not available in the first version on the chip. The Altirock 2 is being tested extensively right now and is close to the specification. The design of the Altirock version 3 is well advanced, but needs to wait the end of this test to be put in production. And this will be the first version radared and will include also triplication. Then I will conclude with another aspect. So all this new electronics brings in a new requirement for the front-end power distribution. For example, all this new electronics uses power supplies, supply voltages which are much lower than today one, so 1.2, 2.5. And so many power systems will need to be replaced. The common strategy here is to have a multi-step down conversion. There are usually an AC/DC conversion to a system bus voltage in a rad-safe area. Then this system bus is brought via long cables to low voltage power supplies, which create an intermediate bus voltage here. And this intermediate bus voltage is then brought to the front end where the final step down is done on board by the DC-DC converter and linear regulator. This is the scheme used by various subsystems, and depending on the location, the power supplies might be exposed to radiation and be filled. For example, the large calorimeter will start with the 280 volt, and an intermediate bus voltage of 38 voltage. The power supply will have 4 kilowatt maximum power, and they will relocate it in better accessible location. The final step down will be done either with a custom solution or with the new CERN bipole 48 volt DC-DC converter, which are of the same family of the bipole 12 volt, linkpole 12 volt, which are used elsewhere in Atlas, for example, in the strips. The ITK pixel will use a completely different approach. They will use serial power to reduce the cabling and the material budget. On average, 10 modules will be connected in series to a constant current source up to 8 watts of power, and the 2 shunt LDOs integrated in the front of the chip allow analog and digital voltage regulation. So, conclusion, Atlas is making a significant upgrade to its detector to cope with the ILUMI LHC environment. The trigger has been chosen. There is a good progress in the electronics of all the systems despite the complexity of these upgrades, and many systems, as I show you, are entering pre-production or production. The radiation hardness is a key issue for many systems, and so requires to implement a robust ASIC design and to do an intense radiation test campaign. The foundry crisis is still affecting the ASIC production schedule, in particular in case one has to do an unexpected production. And also the global semiconductor shortage is causing for some components longer lead times, and also this is causing an increase of the component prices. Thank you.
Thank you very much for this very nice review. Are there any questions from the audience?
So for the additional timing information, the precise timing, is it only the HGTD system that provides additional timing?
Yes.
Does that get used in the trigger?
No. No, it's not used in the trigger. It is used, for example, in the luminosity measurements, but not in the trigger. It will be like the ITK after a level 1 accept. after a level 0 accept, the data will be read.
Well, I saw the slide with radiation levels in different apparatus. No, I participated through the first phase of LHC in general, and for us was difficult to put some FPGA, especially in Moon Trigger of Atlas. But the main problem was how to put a safety factor. And in this case, now with the running, these numbers are better than the numbers that we used in the past.
So FPGA are, except a couple of cases, FPGA are in a radiation safe zone. So they are not
Low radiation.
Yeah, so they are not exposed to radiation. Just a couple there are just a couple of occasions, but not the trigger ones. Then, concerning the radiation, there has been an intense studying during this all these years, and for example, also for the silicon, we are using also the data that have been collected during the last run and trying to extrapolate what can.
You have some data.
And
to us was
yeah,
completely
exactly.
blind.
Yes, and in last 2 years ago, there has been a change of all the scale factors. There has been a revaluation of the scale factor. Generally, there has been a reduction of the scale factor because in some cases they were too conservative, the one that were used at the beginning. But in the same case, case, they need more study. For example, I can do you an example. At some point in the past, there was this lot by lot variation, which implied a huge scale factor. Now, this, for example, is considered not a good scale factor. So one has to check some samples of every lot if one cannot get the same lot. So there are a new recommendation. They have reevaluated the scale factors, and sometimes this increases also the number of studies that we have to do.
You've mentioned a lot of technical improvements in this nice and exhaustive overview, but I guess also something must be done on the algorithmic side. For instance, triggering on displaced particles, which is becoming more and more important, which has repercussions at least on the firmware, but probably maybe even on the hardware. Can you comment something on this?
No, so given that we now are sending the complete high resolution data from the tile calorimeter, the Lhc calorimeter, and the muon system to this FPGA here, we can implement also more complex algorithm that we will use in the past, where we had to make trigger towers. We have to compact all the events. So now, using this higher granularity information and with better resolution, given the power of the FPGA, we could implement also more global analysis algorithms, and also use something like what you say, displaced vertices, but of course not at the tracking level, only if we can have something from the calorimeter trigger and the muon system. Tracking information is available only at the event filter level.
Okay, thanks. I think that now we need to move to the next speaker. Let's thank the speaker again. The next speaker will be Valentina Scotti from INFN Napoli, who will be talking about the trigger and data acquisition system for the high energy particle detector on board of the CES satellite.
Però ci respiro così. Ok. Okay. Good afternoon. I'm Valentina Scotti from INFN Naples and University of Naples Federico II, and I don't have the pointer. Okay. I want to thank the organizer for giving me the opportunity to give you a talk about the high energy particle detector on the CSTS-02 satellite. And in particular, today we will see how the trigger acquisition and data acquisition system works. The China Seismoelectromagnetic Satellite Program has been developed to study ionospheric perturbation related to earthquakes. I will first introduce the second satellite of this program, which foresees a constellation of satellites. And then I'll move on the high energy particle detector, which will be hosted on board this satellite. I'll focus my talk on the electronics and in particular on the trigger and data acquisition, trying to give you an overview of the requirements and of the capabilities of the system. I will conclude with the current status of the development and the outlook for the launch. So, this satellite is a multi-instrument, and the total mass of the satellite is 900 kilograms. It will be placed on an orbit of 500 kilometers. The orbit will be analogous to the one on which has been placed the first satellite, which was launched in 2018. But there will have a phase shift of 180 degrees. In order to maximize the timing resolution. The expected lifetime of the satellite is 6 years, and the launch is expected by 2023. HEPD is one of the payload on board, and this is the one dedicated to the study of relatively high energy particles. The main target is to study the spectrum of protons and electrons in the Van Allen belts. The main difference with the HPD-01, which is on board the first satellite, is that this time we will be full-time operational. So we will acquire data even at the poles. And this is something not so common in satellites studying fluxes of particles. HPD-02 will detect cosmic rays in the energy range between 3 and 300 MeV. And for each particle, the instrument will be able to identify the kind of particle, measure its energy, and the pitch angle. We have to maximize the geometrical acceptance, but respecting the restriction about the weight and the power budget, because of course this is a satellite mission. In this table, you can see some of the main parameters of the instrument, and as you can see, it's a very compact instrument, which the total mass will be below 45 kilograms, and the power consumption has to be below 45 watts. Of course, the data budget is limited too, and we only have 100 gigabit per day. The instrument is actually composed by several sub-detectors. The first one is a trigger, which is composed by 2 crossed layers of segmented plastic scintillators. Then we have a tracker, which is actually sandwiched between the 2 layers of trigger. And this is followed by the calorimeter, composed by 12 layers of plastic scintillator and completed by a LISO, which has a higher light yield, and so it allows us to extend the range. The system is contained in a VITO. which surrounds the calorimeter. Each plastic scintillator is read out, each scintillator actually is read out by two photomultipliers, which are placed on the corner for redundancy. The main improvements on with respect with HPD01 are the trigger and the tracker, which have been totally changed. So I'll describe them in more details. The trigger is composed of two crossed layers of scintillators. The first layer, trigger 1, is segmented into 5 counters, and this is in this way to match the tracking modules. So we have one trigger bar for each tracking modules. It is a very thin scintillator, only 2 millimeters, and this is done to minimize the multiple scattering and also to allow for a low threshold. The second layer of trigger is segmented into 4 thicker layers, and they are thicker to give a good measure of the energy which can reach the second layer. The trigger logic will not be based only on the signals coming from the 2 layers of trigger, but they will be based also on signals coming from the calorimeter. And this allows us to have a flexible trigger logic and to select several kinds of particles impinging our detector. This system has to be well designed and strong in order to select interesting particles when we are at very high fluxes, like at the poles. The tracker is based on a monolithic active pixel sensor, and this is the main innovation compared to HPD01. We have 3 different sensitive planes and 5 independent tracking modules. The controller readout is based on ultra-thin flexible printed circuit. This is the first time that this kind of tracker is used in space. And of course, we had to deal with several challenges in order to make it usable in space. The support has to be as light as possible in order to avoid multiple scattering, but at the same time, it has to be strong enough to support the launch acceleration and vibration. This system will work at only 6 millibar, so we are in vacuum basically, and the tracker was tested also for heat dissipation in vacuum. Finally, we had to meet the requirements on the power budget, and this was not an easy task. Anyway, the electronics of the system is based on 4 boards. We have data acquisition electronics and managing and control electronics. The data acquisition electronics comprises both the data acquisition chain and the bias distribution for the detector. We have a board which does the readout of the tracker, and another one which reads out all the scintillator detectors, so the trigger, the calorimeter, and the VITO. And this is called trigger board and will be the main focus of my talk going on. All the electronics is in a dedicated box, and the communication between the boards is done via space-wire light protocol. Each electronic board has an embedded hot and cold redundancy. The temperature range for this system is a wide range, and all the electronics was qualified between -30 and +50 degrees. The system is designed to cope with the maximum data transfer rate that we have from the satellite. The main functionality of the trigger board are summarized in this slide. We performed the readout of all the 64 photomultipliers of the on board, and we use 2 ASIC. We use the CityRock by WeRock, and on the board we also do the digitalization of the signals. The CD-ROC allows us to have configurable gain, 2 lines of configurable gain, and also to configure a different trigger threshold to optimize the acceptance. We will use different trigger configuration to match different orbital zones. And for each trigger configuration and each PMT, we will have dedicated rate meters. Going from HPD01 to HPD02, we had to change the trigger logic to deal with the increased trigger rate at polar region. So we decided to implement also some prescaling. And due to the larger amount of data acquired, we also had to do onboard mass memory for buffering for the data. This is the block scheme of the board, and this is the electric model, which we extensively tested in the last year. This board is custom designed, and you can see that all the 64 channels are in common for the 2 sides, for the hot and cold sides. And on each side, we have an FPGA, 2 ASICs, and 4 ADC. We decided to use a signal coming from the last dynode of the photomultipliers because these CD-ROC are designed for silicon photomultipliers. So in this way, we reduce the power consumption because we don't need the inverters on board. And we also use a coaxial cable to improve the noise immunity. The signal coming from the photomultipliers goes through a conditioning stage and then goes through the CD-ROC. The fast trigger lanes from the CD-ROC are read out by the FPGA, which then decides if there is a global trigger, which is used both to acquire the analogic signal from the CD-ROC and to give the trigger to the tracker. We performed an extensive characterization of the readout chain. Here you can see the study that we did on the threshold. We were able to see that we can detect a signal as small as what is equivalent to 1/3 of an MIP, which is 17 millivolt at the entrance of the board. And these are some configuration parameters that we choose for our system. Here you can see that the board has a very linear response with the parameter that we choose, and that we are able to separate 1/3 of MIP. And now let's dive more into the trigger. The message that I want to give you is that we have very different fluxes coming on our board. This is the trigger rate measured by HPD01, which is currently in orbit. And you can see that the fluxes varies of 6 order of magnitude. So we have to choose a trigger configuration which allow us to take measurements in each part of the orbit. And this is a simulation for HPD02 in a similar configuration to the one that was used to take data here. So you can see that the simulation is quite consistent with the data taken from HPD01. And from this simulation, we were able to draw some trigger rate map using different configuration. And you can see that on the South Atlantic anomaly, we can receive up to megahertz of trigger. But we have to guarantee that the data acquisition is performed with at the kilohertz rate, because that is the amount that we can transfer to ground. And we were able to see that we can select a trigger configuration which allows us to not only collect data on the South Atlantic anomaly, but also to trigger on particular particle in this area. As I said, we will implement a concurrent trigger, and the lower threshold is the one that is the particle which only hit the first plane of trigger, and then we can have particle at higher energy which crosses the whole system. And of course, the trigger rate map are very different for these two configurations. You can see that using the trigger 1 configuration, we have megahertz rate of trigger, while using a more penetrating configuration, we can reduce the trigger rate to something that we 10 to the 3 in the South Atlantic anomaly, and up to hertz at the pole. So something that we can really acquire. Each trigger configuration is prescaled to match the amount of data that the instrument can process. And of course, these configurations are optimized after scientific requirement about the field of view and also the kind of particle hitting the instrument. And I'm going to conclude with like a serendipitous slide because in the last few years, the multi-messenger is something that all the astroparticle experiments are trying to do, and we explored the possibility to study gamma rays with our system using the Lhc crystal that we have at the end of the calorimeter. The first thing that we had to do is to study the radioactivity background from the LISO. And we we saw that the effects are negligible above 2 MeV. And so we will be able to measure photons at this energy. Here you can see the sensitivity to gamma ray above 2 MeV compared with the one of instruments which are currently acquiring data in that, at that energy, basically integral and Fermi. And based on this study, we decided to implement also a trigger configuration dedicated to gamma rays, which will be tracked on a time basis of 10 milliseconds, because this will allow us to also detect gamma ray bursts if we are lucky. And again, if we are lucky, we can maybe detect 10 gamma ray bursts per year. Finally, I want to conclude with our timeline. This instrument and this system were developed starting in 2018. So after the launch of the first launch was successful, actually. And since then, we have been also testing the system, the electric model. Now we are the qualification and the flight model are under production, and we will test them in thermal vacuum, vibration, and min test. And the flight model delivery is scheduled for October for a launch, which hopefully will be in 2023. So, thank you.
Thank you very much for your nice presentation. The presentation is now open for questions.
You have FPGAs and ASICs in the electronics.
Yes.
So you must be subject to single event upsets, and that should also depend on the rate where you are, in which region you are. So how do you handle that?
We have hot and cold redundancy in case of total failure of the system, but our runs are very short, so the possibility is we reconfigure the FPGA and the ASIC every 2 minutes, actually.
And that's independent of the position?
No, it's okay. We are that's independent from the position, meaning that the run is the same length in any place of the orbit, but the amount of radiation, of course, is dependent from the position. So we have more on the South Atlantic anomaly and at the poles, but the one that is currently in orbit is switched off at 60 plus and minus 64 degrees of latitude. So it's switched off at the poles, basically.
Okay, but still, what's the rationale for having the same length of run everywhere? Because I mean, if you reconfigure often enough on the poles, and in the South Atlantic anomaly, you're
Yes.
configuring much too frequently in the other regions.
Yes,
right?
but we also configure differently for according to the place in the orbit where we are. And in 5 minutes, you go from the equator to the South Atlantic anomaly, so you really need to change the configuration of the ASIC, basically. Because, okay, where is it? Okay, this is the orbit, and we do one orbit in 1 hour and a half, basically. So we cover there. I don't know if I was clear.
Other questions?
I have a couple of questions, very quick. Is the sensitivity, which is the minimum electron energy you can detect?
3 MeV.
Because it seems to me a little bit too low with these thick scintillators. And the second point?
Yes, because for that one, we only use the first layer of trigger. We only require trigger 1.
Okay, so 2 millimeters is.
Yeah.
And second point, wouldn't be better to look for photons with Compton on the silicon detectors, which would be much easier to. The last slide about.
Well, okay, this is not our main
yeah.
physics.
Yeah.
So this is something that comes for free, given the instrument that we developed. So,
but Compton on the silicon would be.
But the silicon is read out only when you have a trigger on the calo. So otherwise it will consume too much power. So we cannot keep it always on.
Yeah. And finally, all the photomultipliers are read out by on the last line, right?
Yes,
yeah.
all of them.
So, but this is AC coupled, so isn't the baseline fluctuating? And
no, not really. It's really stable. I mean, this is the PCB of on which is the photomultiplier is placed. It was developed by the ENFN division of Bologna. And they performed a lot of study also on the where we were taking the signal, and it's really stable.
Okay, thank you.
One last question.
You have quite a different data rate if you're in a South Atlantic anomaly and outside. So you change the pre-scaling of your trigger to get about the same data rate.
Yeah.
Do you pre-program the pre-scaling rate according to your map, or do you dynamically with like a PID
no,
loop
we have
adjust
it for orbital zone because we cannot risk that there is a slight change and then we lose it.
So you pre-program it?
Yeah.
Okay.
For orbital zone.
Yeah. Okay, thank you.
Okay, then let's thank the speaker again. And it's now time for the poster review, which will be given by my co-chair Martin Grossman.
Okay, so I have the task to give an overview of the posters for this session. And as we heard in the introduction by Lodovico, this was quite a lot of posters, actually 57, but one was not uploaded, so 57, 56, but it's really quite a large number. And I have just a bit more than 15 minutes to present this here, so I had to make a selection on the posters. Before we get into this, let's take a look at the statistics. It's quite interesting. This session is front-end, data acquisition, trigger, data processing, and it's quite well distributed over these topics. And for the large chunks here, this has been broken up into the applications. We see it's always the particle and nuclear physics that are the largest part. We get quite a lot of astrophysics, and here a few medical applications, and then here astrophysics and neutrino experiments. The statistics was provided by Ludovico. And he also made the second statistics about where the posters come from. These are two different graphs. This here is the country of the primary authors institution. So you see many European countries, but of course the by far largest number is Italy. And then there's another statistics here. It's the posters with the authors affiliated all from the same country. So one contribution with authors all from Germany, one with all from Russia, 12 with all from Italy, and international collaborations is when there are more than one country involved. So really, it's an international society we are talking about here. So I try to go through the posters that I have selected, and actually I'm starting with the SCT telescope, which we heard in the first talk of this session, and there were some there was a camera, and the readout for the camera of this telescope developed. It's 11,000 pixels. It has primary and auxiliary modules to separate digital and analog channels. Challenges here are long cables. This observatory here is spread out over a large surface. There are size constraints, and the device is still in prototype testing right now, but the schedule, which is outlined here, is that the production will start this summer and the implementation will be at the end of this year, so quite ambitious. Connected to this readout of the camera is this smart ASIC, which is the SIPM readout, and there were extensive quality assurance tests made to test that the production of this ASIC is working correctly. And it turned out that here the fallout rate, the bad ASICs were just 1%, which seems to me very low. And they show good linearity. We will get back to ASIC testing a little bit later with two other posters. Coming to physics, particle physics experiment. This is an experiment at Fermilab, the mu2e conversion experiment, which is a lepton number violation search. So for these experiments that are prohibited by the standard model, you need high statistics, you need to take a lot of data. In this case, it's 7 petabyte per year. And the trigger and the data acquisition of this mu2e experiment is based on OTS Daq, which is sort of a general purpose data acquisition system of Fermilab. This link here, unfortunately, if you want to look this up, it asks you for a login to Fermilab, but if you Google OTS Daq, you find information about the system. The slow control is done with epics. So I find it interesting that really standard tools can satisfy the requirements for such a new experiment. And from the same experiment, there is a poster on the event display. It's online and offline event display, which is needed to monitor during the data taking. It's to help interpretation of the analysis for the offline. And it's important for public outreach, showing the events that you can reconstruct. Here the technology or the software framework is based on these two packages, which are graphic tools that are based on Geant. So this also means that you can use the geometry that you have programmed in your Monte Carlo to provide the framework for these slides. So again, it's use of standard software which is done for a completely new experiment. The next board is also from an experiment that has to do with lepton flavor violation, the MEC2 experiment at PSI. It's a combined effort between PSI and the ENF and PIsa. And after 10 years of development, this board or this data acquisition system, I should say, is now working properly and taking the first productive data. It has a custom-made crate, so it's not using VME, but it's really something developed for them. The whole system has impressive performance. The numbers are here. And I think this is something which could be very interesting for other applications. The poster talks about beam scanners, calorimeters, drift chambers. And related to the WaveDAQ or to the Mach2 experiment is the talk by Marco Francesconi, which will be in this session right after the coffee break. And if you go to see the poster, you will also be able to see some of the hardware that Stefan Ritt has taken here to the conference. Coming to another experiment which happens at GSI, it's the food experiment. It's about fragmentation of carbon and oxygen nuclei. The interest there is hadron therapy, where these nuclei are used for radiotherapy, so you're interested in the fragmentation. And this here is the design of the trigger. This is here the better schematic to see this. So the nucleus comes from here. There is first a start counter, then you have the target, and then the nucleus either fragments or continues straight. And only 10% of the nuclei do this fragmentation. So you have to find out these instruments. And usually when you get a large signal here in the central region of that second part of the detector, then you have discovered, then you can distinguish between the primaries and the fragmented events. Now we come to some of the LHC experiments here for Atlas. High granularity to cope with the high luminosity and fight against pileup. This is a feature which we see in many detectors. And here, in order to cope with the high granularity, Atlas is developing a peripheral electronics board. In this phase here, it's a demonstration of the basic functionality of this board. And this interesting aspect is that they paid attention to be able to use commercial ASICs. So if they have some problem with the ASICs they are developing, then they might fall back on chips that are commercially available. So one way to cope with this crisis. The PHASA experiment is a little bit a neighbor of Atlas. It's search for long-lived particles. It's 480 meters away from the Atlas interaction point, and the signal are two photons in the TeV range, and they are separated only by 200 microns spatially at the point of the detector. So the readout is also happening with a dedicated ASIC, and at the moment they are still in the very early testing phase of the layout with simulations. And we come to CMS. DuckPath is the readout of the Serenity boards in CMS, which are connected to the level 1 triggers. Each board has 144 optical inputs with 25 gigabits. It's a modular design, and it has the possibility for flexible configuration to meet the timing requirements. LHCb track reconstruction. It's an upgrade of the tracking system. The hardware trigger that was in use up to now is not fast enough anymore, so it's replaced by a software trigger that will run on GPUs. And the tests that expect a tracking efficiency of 80 to 90%, depending on the energy, and a throughput 170 kilohertz. And one slide which is connected to bolometric detectors. As we learned yesterday in the talk of Claudia Nunes, the second generation of these bolometers, they now have particle identification. You can distinguish between the phonons and the photons. And because the different signal rise time, there are new requirements for the data acquisition. So here they have devised this digitizer board with 12 channels, low power, little space. Data stream is transmitted over UDP, and it is right now operational in a test setup. We come to ASICs and ASICs testing, and this is an interesting example from CMS. It's a chip that is the CBC3 chip, which is connected to the 2S modules in the trigger of CMS. And this ASIC was developed over many years, and the pre-production was done in 2019. And it turned out that these wafers, which had several chips on it, have problems. If you look here at these patterns, green are the good chips, red are the bad chips, and you see funny patterns that are circular. Here, many chips in the center are bad. Here, it's more on the outside. They were looking really for a long time to find out what is the reason for this. And it clearly had to do with the production process of the ASIC. In the production process, there is some polishing involved. And if the wafer is not completely flat, then you get these kind of patterns. And the developers there, they found it very difficult to interact with the foundries because these are very big organizations. They are not interested in changing anything of their process, so it really took a long time to cope with this problem. The original author of this poster is not here, but Geoff Hall is available for more information on this topic. Another example of wafer testing, so this, you see, this is much more a random pattern. So there was not such kind of detector or of production problems. Here, the yield in good chips is 73%. It's written somewhere on the poster. Yeah, it's here, 73%. Cluster counting with FPGAs is an example here. It's again high granularity, and you have to do the tracking. This is the summary slide, and I find it contains quite a lot of information for a summary slide. So what it's really about is you have the detector, the ADC, and then you have the FPGA that does the calculation of the tracking, and then you carry on to the proper data acquisition and the storage. So by doing the tracking in the FPGA, in this example, they say they gain a factor of 100 in reduction of data. And for details on the algorithm, you have to refer to the poster. This is a similar approach used in a baryonic matter experiment, the digitization, and then here the FPGA, in this case it's a Xilinx, does the data reduction. In this case, you see 80%, this means it's about a factor 10, the reduction. So this has to do with the specifics of the detector, that it's different. Machine learning techniques. This is an example from Juno, the underground neutrino experiment. And they use ML to reconstruct the neutrino energy from the input is the charge from the photomultiplier, the timing, and the position. And they find that they can reach the requirement on the energy resolution, and they say they have a high computational speed, but it's not really quantified what this means. Now more to the software side. This is an interesting tool, HDL on JIT. So it addresses the problem of firmware development in collaborations, the traceability of your firmware. And it's based just on a set of Tcl and shell scripts, so minimal overhead. and has integration with various IDEs, so seems like quite an interesting tool. Now 2 examples that are from the medical physics application. This here is the data acquisition system for a detector that is used for patient-specific quality assurance. This means in radiotherapy, you measure the dose distribution in a dry run before you use this therapy plan on a patient, just as a cross-check that everything went well. There was a specific talk on the detector in another session, and here it's a description of the data acquisition system. It's based on scintillation detectors that are then read out. It has timing protocols, FPGAs. So for me, the point here is it's technology which most of us know very well, but it's an interesting application for this purpose of quality assurance in the medical field. From the same collaboration, also in this session, a pure software project. This is the use of deep learning for segmentation. Segmentation means on a computer tomography image, you outline the region that has to be treated in radiotherapy, that is the region where is the tumor. This is usually done by medical doctors, and it turns out that when more than one medical doctor does the same contouring on one image, the result is not always the same. The authors give you one example, 2 doctors drawing the outline of a tumor in the brain here. The green, the red and the yellow line are 2 different people, and you see the volume is slightly different. So this poster addresses the question, can deep learning, can artificial intelligence beat humans? I think the result is not yet there. And to finish, 2 posters which have quite interesting application. This here is the development of a chip in CMOS technique, which is called a time spot. It's designed for high rates and high track densities, and you need timing information on pixel level. So it's a CMOS with a 32 by 32 pixel matrix. Each channel has an analog front end, has discriminator, has a TDC, timing resolution 20 picoseconds for the TDC or 40 picoseconds for the analog. And this is one first iteration, and they are already working on the second one. This has been motivated by LHCb requirements, but this could be a chip that is interesting for many other applications as well. And the last poster, witch hunters. This has to do with the detection of gravitational waves. To reach the sensitivity in this kind of experiments, you must suppress the background, the noise event called glitches. The authors of this poster here, they use citizen science to cope with this problem. So they have a network of volunteers that look at these identified noise events and try to characterize that. And the result of this characterization goes as training data sets for an automated analysis using machine learning. So the human input goes into the machine learning to make this analysis later automatically. And this concludes my survey over a few of the posters.
Okay, thank you. I think that now is time for the coffee break. And we convene in, okay, don't know, 10 minutes? 20 minutes, okay, okay.
system that you can maybe see here is a tightly coupled trigger and data acquisition system, and so it's a little bit hard to disentangle the two parts of the same system. So let me start with a very, very brief and kind of corner part of the slide introduction to the physics that we are doing. So we are looking for this decay of the muon that you can grasp that violates the lepton family number, and this has a very big implication for physics because, as you know, the standard model does not foresee this kind of decays because the lepton couples only within the same family, therefore conserving the number of leptons in the same family. But the neutrino oscillation show that this kind of processes can happen, so the lepton family are indeed violated. And this is the contribution that we have for the standard model to the mu gamma decay, which is way below the experimental limit, so the experimental reach. So any evidence of this kind of decays is a direct evidence of new physics. Let me start with where we are. So the former iteration of the experiment I'm part of actually has the world best upper limit in this this decay, which is 4.2 times 10 to the minus 13 at 90% confidence level. And in these last years, the collaboration went through a very big experimental upgrade, which actually also kind of changed the name from MEG1 to MEG2. And we plan an order of magnitude increase in the sensitivity, therefore going down to 10 to the minus 14. In order to put an upper limit on the branching ratio at this kind of level, we need to observe an enormous amount of muon decays. So we'll need to collect, because of the reconstruction efficiencies and angular acceptance, 10 to the 16 muon in the 3 years of planned data acquisition. And even using the world's most intense continuous muon beam, which is available at Paul Scherrer Institute, and produces 7 times 10 to the 7 muon per second, we will take all of the 3 years that we are planning to run. Because of this very high beam intensity, we have, in addition to the signal, two other processes of background. The first one is the physics-induced one, which then scales with the beam rate, and it reaches the signal when the two neutrinos carry out a very small amount of energy. And then we have the accidental background, which is the coincidence with an high energy positron plus a photon that comes from some other processes like this one or other sources of photons. And since this is an accidental coincidence, it scales with the square of the muon rate, and given that we are running a pretty high beam intensities, even if we have very good time resolution, this is the dominant source of background. So just in one slide, I will go through the detection strategy for an experiment which is directly tailored to measure this decay. So the muon are stopped at rest at the center of the experiment to exploit the very easy two-body decay kinematics, and this produces a very high pile-up environment at the center of the experiment. We have liquid xenon scintillation calorimeters that reconstruct all those observables, so the energy, the angle, and the time of the photon. But these cover only a reduced part of the solid angle, like 11%. And on the other side, the positron bends in a magnetic field and are tracked by a very light drift chamber before it hits an array of plastic scintillators that gives the time to the positron track. All of this happens in a magnetic field which is non-uniform, so to remove as much as possible the beam rate. All of the detector must provide very high resolution, charge and time reconstruction on all of the channels to cope with the high occupancy that we have in all of the channels. And to accomplish this, we opt for the digitization of all of the signals with very high sampling rates, At the moment, we are running at 1.4 gigahertz of samples, but we can run maybe a little bit higher in the future. This produces the full waveform that can be stored for offline processing, and therefore we can iterate on the algorithms that we use for noise rejection, pile-up identification, feature extraction, and so on. How do we do this? Of course, doing this with commercial fast ADCs is not feasible because we need 4,000 channels, more or less. And so it's just too slow or too costly, depending on how much you can afford. And for this reason, already MEG1, the collaboration used the DRS4 ASIC chip. DRS4 is an analog switch capacitor array, so it behaves like an analog memory with a depth of 1,024 samples, and it's developed at PIsa. And this provides kind of a snapshot of the signals before the trigger time. So all of these capacitors are connected to the input signals by these ring oscillators. And when a trigger arrives, the content is frozen and downloaded by as lower external ADCs. This put a very strong constraint on the triggered system because the decision must happen before the full revolution of the storage capacitor happens, therefore overwriting the pulses that generated the trigger. Running at 1.4 gigahertz, which is the current one, we have a constraint on the trigger latency to be smaller than 731 nanoseconds. The current implementation for MEG2 of this chip is known as the WaveDAC system, and its main board is called WaveDream, which is a 16-channel DRS4 readout module that in a very small footprint contains 2 of these DRS4 chips for 16-channel data acquisition, and also includes the analog amplification and biasing of the SIPMs that are extensively used in the MEG2 upgrade, especially for the liquid xenon timing counter. For more details on this part of the data acquisition, I wrote here a poster that you can definitely ask more information. But how to reduce this the event rate? Because using full waveform digitization actually has the impact of having a very huge event size. We have 12 megabyte event size before the compression, and this reduces by factor 4 when we apply compression and data reduction. But this still is like half a petabyte of data to be stored every 3 months at a reasonable 20 hertz DQ rate. So in order to select this, we look at the physics observables. Of course, the photon energy is an important one because for the signal is monochromatic at half of the muon mass, more or less. And for the accidental background that I said is the dominated one, is decreasing. So this is definitely a good variable to cut on. Unfortunately, almost all of the variables that has to do with the positron is very hard to do at trigger level because the cylindric drift chamber, which is the heart of the tracking system, cannot be exploited because of the drift time that is present in the detector. So the other variables that we can use is, of course, the time coincidence of the 2 particles. And then we have another possibility that I will present you later. In summary, the requests we do are 3. The first one is the estimate of the gamma by the signals coming from the liquid xenon, and we call this the Q-sum trigger. We have the T gamma by comparing the heat in the xenon and the heat in the plastic scintillators, and we call this the time trigger. Then, since we really know the topology we are looking for, we know that for a photon that goes in a particular region of the liquid xenon, the positron has to go to a particular region in the timing counter. And we call this the direction match. So the first Q-sum trigger has a reduction factor of 100 because the energy spectrum is decreasing there, and this provides a pretty big reduction factor. And the other one still helps in bringing down the DQ rate. So let me go, first of all, to what the trigger sees. So each of the WebDream board contains, on top of the DRS4 chip, a dedicated ADC, which is also used to read out the chip, and a discriminator path, which kind of bypasses the DRS4. So if it's possible, we just use the comparator, therefore cutting the conversion latency, which takes 100 nanoseconds, so it's not negligible at all in the trigger latency we have. Otherwise, we can use the ADC for charge or time-based selection. For example, for the here you can see an example of signal from the liquid xenon detector, where you can see the pulse recorded by the SIPMs. And in this case, instead for one of the plastic timing counters, we do have the small pulse coming from the discriminator, followed by, after some latency, the pulse recorded from the ADC. How we build the information together, we have a 3-layer trigger tree that converges the information first toward the central board, which is this one, inside of each crate, and then from that one to a full dedicated trigger crate that does, at the end, the final trigger aggregation toward what we call the master trigger board, that then have the complete picture of the situation, the experiment. All of this happens using dedicated low latency serial links because, as I said, every cycle is important for us. So we decided to use shift registers, which have a smaller bandwidth in transmission with respect to gigabit transceiver that are available in modern FPGAs, but has a much reduced latency. So we kind of got back this. So let me go quickly through all of the design. So first of all, the QSUM trigger, essentially we do the weighted sum of all of the channels from the xenon. So we start from the ADC samples, and we subtract the pedestal, which is estimated on the fly. And after that, we apply a channel by channel weight to account for different gain, detection efficiency, and detector type of the detector, and putting this together and using what's available in the modern, in this case, Xilinx FPGAs, especially the DSP48, that allows all of this to be packed in a single slice of silicon in the FPGAs. We can indeed compute this sum in the available latency. And this is what we got. We have two main calibration sources in the liquid xenon detector. One is this CW proton accelerator that smashes a 1 MeV proton on a lithium tetraborate target and therefore produces 2 gamma lines. And this is done like 3 times per week. And you can see here the reconstructed spectrum at the trigger level. And once a year, we do a calibration run using a pion beam that does a charge exchange on a liquid hydrogen target. And from that one, we get 2 calibration line. The overall trigger energy resolution was measured to be 2.4% at energies near the signal energy, which is not far from the 1.8% that can be reconstructed offline. A very quick addendum on the QSUM trigger. We actually can do Q over A selection. In particular, this is useful because we are using noble gas scintillators. And as you may know, they exhibit a different decay path depending on the source of the ionization. For MIPs, like the alpha particles, this is much faster. I mean, the decay time after the heat is much faster with respect to the gamma-like ones. And we use that using 25-point-like alpha sources, which are immersed in the liquid xenon volume to produce localized energy deposit because of the small range of alpha particle in xenon. And this can help in, because we very well know where the energy deposit happens, and therefore can be used at the Monte Carlo, combined with Monte Carlo level, to obtain the quantum efficiencies of the detectors. And all of this can be done at trigger level, and we can select the one with the Q over A selection smaller, and therefore increase the samples of alpha particle and reduce the gamma that we don't want. The second request is the direction match. Essentially, we check a group of SIPMs in the interface of the xenon as a conversion point estimation, and we compare it with the estimation of the position in the time encounter. And this is compared with the Monte Carlo, and the point that you see here in blue are the couples that we expect to fire. So the higher segmentation of the Mag2 detector increase the rejection power of these algorithms in respect to what we could do with Mag1. Here is the slide of the performance for this algorithm. In order to extract the effect, we do a comparison with the physics trigger with what we call reduced bias triggers. And here you can see that for relative angles smaller than 3 steradians, the spectrum starts decreasing. For the time, we exploit the serial links that we have in the Fpgas, and using this we can oversample the hits, and therefore we obtain around 450 picoseconds. We could do better by using other sources of TDCs, but this is enough for us, and we do some averaging depending on the detector types. This is the same kind of ratio. Those are the mu gamma trigger and the prescaled one, and by the ratio we observe a 3 nanoseconds coincidence, which is not so great, but we understood the source of this, and it's due to the very small rising time of the MPPC signals. So this will be cured in the future. So in conclusion, the Mag2 ended its first data taking in 2021. As a data sanity check, we did observe the mu e nu gamma peak in the time spectrum, and this is a clear source of goodness of this data set. And the wave-duct system successfully scaled to its final form, and the trigger system performed very smoothly in the 2021. We are looking forward to the 2022 run. So here, just a few more posters that you can look for the use of the wave-duct. Thank you very much.
Okay, thank you, Marco, for this nice presentation. The paper is now open for questions. Are there any questions?
Hi, thank you very much for the very nice talk. A question. When you, a couple of slides earlier, you show the, yes, here. So there is this factor of square root of 12.
Yeah.
To what is due?
This is just the binning. So this is the bit of the TDC. So since you don't know when the time arrived in the bin, it's just the square root of, because it's flat distribution.
The UV radiation damage to the SIPMs presumably affects the pulse height and therefore at some level the timing.
Yeah.
So how is that reflected into the capability?
So not only the damage, is actually also the depth that has some impact, because it's an homogeneous scintillator. So the deeper the energy deposit is, the more spread is the energy in the interface, the lower is the amplitude, the worse is the time. What we plan to do is to use the PMTs, which have a much faster rise time, and therefore should help in reducing the time of work. Essentially, we have a leading edge discriminator, so we cannot do much for this. I mean, much more than we could.
Other questions? Okay, there are no other questions. Let's thank the speaker again. Okay, the next speaker is Valerio Re from University of Bergamo and INFM Pavia. and he will be talking about the readout chip for the tracking detector of the GAPS experiment.
Okay, so GAPS, or the General Antiparticle Spectrometer, is an international collaboration with institutions from the US, Japan, and Italy. And it's an Antarctic balloon experiment that is designed to detect low-energy cosmic antinuclei as an indirect signature of dark matter. So the instrument is actually optimized to detect with high precision antiprotons, antideuterons, and possibly anti-helium. Now the instrument is under construction. It is preparing for the first flights, which should take place from Antarctica at the end of 2023. The instrument consists of a large area time-of-flight system and of a 10-planes tracker with custom-designed lithium-drifted silicon detectors with a dedicated front-end electronics, dedicated ASIC, which will be the focus of my talk. So first, a few words about the detection principle of this experiment. So actually, the incoming antinuclei first go through the time-of-flight system, which measures energy, deposition, velocity, and timing. And then these antiparticles are slowed down in the SILI tracker, where they are captured by the target material, by the atoms in the target materials, forming an exotic atom. So they replace an electron in the orbital shell of the silicon atoms, with the antinucleus orbiting the nucleus of the target material. Then these exotic atoms are unstable, of course, and so they de-excite, emitting X-rays with characteristic energies. And also then the antinucleus annihilates with the target material, producing a kind of star of pions and protons. So the SILI detector has the function of detecting the characteristic X-rays with energies varying in a range roughly between 20 and 100 keV. And also this detector has to measure the tracks of the charged annihilation products. So and this provides identification of the antinucleus and provides rejection against protons and other kind of background. So actually this tracker has these three functions, as I already discussed. So it's a target to slow incoming antiparticles and capture them into exotic atoms. Then it is a spectrometer to measure the energy of characteristic X-rays with a resolution that has to be around 4 keV full width at half maximum. And then also this is called tracker because it has to determine the tracks of the annihilation products from the nuclear decay. So these lithium-drifted silicon detectors are actually large area detectors for this kind of technology that were developed by the Columbia University, MIT, and JAXA, And then this process was transferred to Shimatsu Corporation in Japan. So they are 10 centimeter circular detectors. So you see here on this module 4 of these devices. They are segmented in 8 strips, each is 1 centimeter wide. And also these are thick detectors, so with a 2.5 millimeter thick active area, active thickness. And they can be operated at relatively high temperature, around minus 40 degrees Celsius, which somewhat relaxes the requirement on the cooling systems. Okay, for the readout of this CILI tracker, we have designed and fabricated a readout chip. You see here the layout. It's a chip with an area of about 9 square millimeters. You see here the basic specification. So here we read out 4 detectors, each with 8 strips. So we have 32 channels. We have to limit the power dissipation below 10 milliwatts per channel and operate with a dynamic range extending by about 4 orders of magnitude, so from 10 kV to 100 MeV. And we have to achieve this resolution of 4 kV full width at half maximum with a detector capacitance of 40 picofarad and a detector leakage current around 5 nanoamp. Okay, so we went through a few prototypes, starting from smaller chips with a few channels, and then in 2019 we submitted the first full-scale prototype, and then in 2021 finally the flight ASIC, the flight device, which is called Slider 32 because it has 32 channels and is the CILI detector readout. Now going inside this chip, so you see here in this block diagram that we have first a charge-sensitive amplifier, where probably the most interesting feature is this MOS capacitor in the feedback to integrate the charge delivered by the detector. Actually, this is a non-linear capacitor which allows the chip to perform a dynamic compression of the range, and I will say you some more words about this later. Then the amplifier is followed by a filter or a signal shaper, and then the peak of the signal at the output of the shaper is detected by a sample and hold. So this sample and hold may be triggered by the time-of-flight system, so may receive an external trigger, or we may operate in a self-trigger mode by detecting the time at which the peak occurs with a differentiator followed by a zero crossing discriminator, which can be used to trigger the sample and hold on the peak of the signal at the output of the shaper. Also here you see that we have a threshold discriminator, which triggers the 11-bit ADC that converts the signal amplitude and then sends the information to the digital backend. Actually, we have a single ADC per chip, so we have a 32-to-1 multiplexer delivering signals from all the 32 channels to this single ADC. Okay, so a few details about the schematic. So here you see the charge-sensitive amplifier with a complementary folded cascode architecture with a local feedback in the cascode and a regulated cascode load. We did also some noise studies on this technology, and you see here the noise voltage spectrum of the input transistor, the input NMOS in this circuit as a function of frequency. Actually, it's interesting that we measured a relatively higher 1/f noise with respect to the typical simulation models. And so this gave us some excess noise that we measured on the full chip. Anyway, we are still able to stay inside the specifications. In the preamplifier, we also have a charge restoration network, which is based on the classical Krummenacher architecture that is able to compensate for the sensor leakage current up to 50 nanoamp, which is much higher than the expected current from the sensors, but this may also allow to test the device at temperatures that are higher than the nominal minus 40 degrees. And also here we have a structure with current mirrors that allows us to measure the sensor leakage current. Then a few words about the dynamic signal compression. As I said, this is based on a MOS capacitor in the feedback of the preamplifier. So at small signal levels, this operates below the threshold voltage of the MOSFET. So the capacitance is just the gate overlap capacitance with source and drain. Instead, when we have a large amplitude signal at the output, there is a gate to source voltage that goes above the threshold voltage of the transistor. So we have a channel between source and drain, and so we add the capacitance from gate to channel. And so we have a small feedback capacitance, so high gain at low signal amplitudes, and we have a high feedback capacitance, so low gain at high signal amplitudes. And so we implement this kind of approximately bilinear characteristic. So you see here the amplitude of the signal as the output of the charge-sensitive amplifier as a function of the incoming energy. So we have high gain at low energy and low gain at high energy. So, of course, this Krummenacher feedback operates in a non-linear fashion for large signal amplitudes. Also has some complicated return to baseline, considering that we have this non-linear feedback capacitor that has to be discharged. But anyway, we are able to completely recover the baseline in less than 10 milliseconds, which is adequate for this application, where we expect to have a hit rate below 1 Hertz in each channel. So you see here the shaper, which is a classical CRRC squared filter, where we can tune the peaking time from 300 nanoseconds to 1.8 microseconds. Then we go from the shaper to the sample and hold, which holds the peak value of the signal at the output of the shaper. So this is a differential sample and hold. So this provides a differential signal to the input of the ADC, so that we acquire immunity from noise coming from the substrate and from the digital part of the chip. And then we have finally the ADC, which is based on a hybrid digital to analog converter in a successive approximation architecture for this ADC. So this means that we have this Daq is divided into a resistive section and a capacitive section to optimize linearity and matching between components and the total area of the circuit. And so actually you see that we were able to perform tests of this ADC as a standalone block using as the input the temperature sensor that is located on the chip. And actually, we had some limitation due to a capacitor, a mismatch between capacitors in this Daq that is actually higher than what is provided by the models in the design kit of this technology. This is a 180 nanometer process by TSMC. So this actually limits resolution to about 10 bits with an average effective number of bits of 9.8, which is anyway adequate for the required resolution for this application. Actually, we could do better than this by performing a calibration of the ADC, but this requires an additional complication in the design that is not strictly necessary. So you see here a slide with the noise. So the equivalent noise charge, full width at half maximum, so measured in kV as a function of the shaper peaking time. And you see that here in a region between 500 and 800 nanoseconds, we get very close to the required 4 kV resolution. Also, you see here on the right this plot. So we have, for this test, we have connected some channels here on the left to a detector simulating capacitance of 40 picofarad. And we have other channels that are instead not connected to anything, so they operate at 0 capacitance. And you see, of course, the higher noise when we have this 40 picofarad capacitance with an average of 4 kV resolution. And also, we have a digital to analog converter for a fine trimming of the threshold in each channel, so that we can operate with the required 20 kV threshold or even somewhat below that with just a very small percentage, well below 1% of hot channels. Okay, let me go to the conclusion. So we have this fully functional without chip, without the lithium-drifted silicon tracker of the GAPS experiment. Chip production was fully successful, and now we are currently testing all the front-end boards with the ASICs in order to then fabricate and build the flight instrument. And we plan to make this first flight from Antarctica with a balloon at the end of 2023. Okay, that's it. I will show you a slide of the great people in the GAPS collaboration as a final conclusion. Thank you.
Thank you very much, Valerio. The paper is now open for questions.
You have with 40 picofarads about 1,100 electrons noise, which I find is a good number. What astonishes me is that the 0 capacitance noise. Can you comment on this?
Why it is so high?
No,
what was the question?
Yes. I mean, I thought that was obvious. The slope from 0 capacitance to 40 picofarad seems to be quite small.
Yeah, yeah, right.
And so the offset is quite big. So question is why, and do you understand this?
Mm-hmm. Yes, the measurement that you saw, let me go back. I think this is done at about 800 nanoseconds, where we already have some contribution, some sizable contribution from parallel noise coming from, mainly from the feedback, from the Kuhn-Menacher feedback, and also somewhat from the leakage current of the sensor. And so this is why this becomes a dominant contribution at 0 capacitance. Okay, this is why the slope appears to be relatively small.
How do you keep it at minus 40? Is there an active cooling system, or you just assume it's cold in the balloon?
Well, there is this technique which is called oscillating heat pipe, which I understand, I mean, I'm not an expert on this, but I understand it's in an original technique for operating at these temperatures without having a large burden on the balloon that is then carried by that carries the instrument. It's a passive system, yes.
I wasn't sure how many channels you have to build in this system, but for this non-linear amplifier, do you have to worry about uniformity from channel to channel, or can you calibrate each channel?
Well, of course, we are aware of this. We have the possibility to tune each channel, so there is a reference voltage in the feedback that can tune the back point of that bilinear characteristic. So we can do this on a channel-to-channel basis. So with a calibration procedure, we can tune these characteristics on all the channels. Also, this characteristic is also somewhat sensitive to temperature, but we have also implemented some features in the circuit that reduce this temperature sensitivity. So we have taken care of this, so that these effects are reduced down to an acceptable level.
Okay, we need to move to the next speaker. So let's thank the speaker again. Thank you. The next speaker is, and the last of the session, is Marco Battaglieri from INFN Genova. He will be talking about streaming data acquisition system for electron scattering experiments.
Can you hear me? Yes, you can. Pointer. Okay, so I'm going to be the last, so I will try to be short. Streaming data acquisition system for electron scattering experiment of the next generation. Just a few words about the difference between a triggered DAQ and streaming DAQ. Should be self-evident, but it's better to state the base. So traditional trigger is expecting to get the data out of the detector, and you delay the stream of the different signals until part of the detector give and provide a local trigger. And then when everything is done, you're ready to get your data and store them. Pros, it works. We are based on long experience of many experiments that works with the traditional trigger DAQ. Drawbacks, there are some drawbacks on it. Only few information from the triggers, and also the trigger logic used usually based on Fpgas is very difficult to be programmed, especially by physicists. You need to have some support by engineers. It's more complicated to work with. And also, it's very difficult to change the trigger scheme as soon as you have something working. For the streaming readout, is a kind of different because you have the stream of data are digitized and continuously recorded. So there is no delay. No, you don't need to bufferize your signal and decide. In principle, you store them, and let's say real time, you decide if you want to keep or discharge the data. Obviously, this has many advantages. All channels can be part of the trigger. You can have a very sophisticated trigger or filtering, if you like, algorithms. And also, you can scale the system very easily. The drawback in this case is the opposite as for trigger, that there is no much experience on streaming readout. So you have to prove that everything works as expected. I mean, in principle, it works, but you want to be sure that since you fail in the trigger, obviously you fail the experiment. So the requirement for a streaming readout is for sure for the next generation of high luminosity experiment that are usually limited in bandwidth for the DAQ bandwidth. You want to increase it, and also reduce the data size, not only because you don't have the capability of storing data, but the problem is then all this huge amount of data needs to be processed offline, and so it takes time. So if you can save time and do a smart selection at the level of the trigger, this is going to save a lot of time later on. Obviously, the streaming readout is going to shifting the tagging and filtering from the front end, so from the hardware level to the software, to the back end. And so this can provide, you know, an optimized real-time, rare or exclusive channel selection. You can use high-level languages rather than VHDL or any other FPGA language. And also, you can take advantage of existing CPU or GPU farms in a very straightforward way. And in particular, I'm thinking to use machine learning or AI that obviously can also be implemented at FPGA level, but it's much more complicated. You are not going to use the entire set of libraries already available for offline processing. And in principle, at some point, we are going to also use quantum computing. Why not? If the network is fast enough, you can move your data and have your tracking on the fly, mainly, with the power of quantum computing. Then, as I already mentioned, you can scale it, you can add new channels, or you can change the trigger configuration, since this is just you know, a C program or C++, Python, whatever you like. It's very easy to change the way how you trigger your data. And obviously, there are many nuclear physics and high-energy physics experiments that are adopting the streaming readout scheme. At CERN, we know, LHCb, for sure, ALICE, we will listen, I mean, we had some presentation about it. But also in FAIR or DAISY, and in US, Brookhaven with Super Phoenix, and JLab with experiment of this generation and the next one, in particular also for the future, the electron-ion collider. So I'm going to mainly referring for the present of electron machine at Jefferson Lab. This is a 12 GeV machine with high luminosity. It's 100% at duty factors, you know, medium energy, but a lot of data. We are talking about and luminosity usually in the range of 10 to the 35. But with some experiment in the future that want to hit up to 10 to the 39. So it's going to be really a huge amount of data that you need to select or process almost real time. And there are 4 experimental halls providing data equipped with standard detectors. All B were class 12 sitting, Hall D with the GlueX detector, and all A and C are using spectrometers. That, I mean, even spectrometers with GEMS, for instance, are producing a huge amount of data. I mean, much more than what people were used in the past. And there are other experiments for the future expected, like Muller or SOLID, that are really pushing the luminosity up to, I mean, values that were really unthinkable up to a few years ago, like 10 to the 39 per square centimeter per second. So it's a huge amount of data that you have to deal with. And same thing for the electron-ion collider. The electron-ion collider is the next machine that is going to be built in the United States. This is, just to give you an idea, is about 1,000 times the luminosity that Hera at DAISY had a long time ago. This is a collider, electron and nuclei. And I think that the physics case was approved, and the process to have it done is on its way. But it's clear that the data acquisition will be streaming. This is quite well defined. And the 3 possible collaborations that are now trying to converge in a single detector, they all adopted in some way the streaming readout concept. This was, you know, discussed, and so it's clear that part of this work requires some R&D, some development, focus on EIC, but not only, also for the other experiment I just mentioned before. And this is done within EIC R&D streaming readout consortium that organize workshop regularly, a couple of workshops per year, where obviously we are not only considering electron machine, but also having the entire experience by LHCb, in particular ALICE and the other CERN experiments. So let me just now go through the different components of a possible streaming readout scheme. You have, mainly three things if you want to prove that your system is working. First of all, you have to assemble a streaming readout system. Second, you want to test it in a well-defined and clear environment, like lab or in a controlled condition, and then obviously test it on beam, because this is where at the end of the day you want to use it. And here are the different components reported. You have a detector, you have the streaming made by the front-end electronics, a back-end, usually software, but this can be also replaced at some point by hardware, by dedicated hardware. But let's say that this is now done entirely by software, and then this is connected to the online reconstruction. And then when you are happy with that, you have a run control that makes everything working, and then you store your data on tape. So as a front end, we use the digitizer. These are the boards routinely used at Jefferson Lab. This is actually a design, is a Flash DC 250 megahertz. They are, kind of obsolete already, but they had no streaming capability. They were talking over the VME bus, but they, with the clever use of an extra board, it was possible to have an optical link up to 40 gigabit per second that makes it, still reusable. Considering that JLab has about 1,000 of these boards, was a good investment to reuse what they had. And also, INFN developed a specific digitizer, very similar, but with the all streaming capability with the zinc FPGA on board, so it's much more powerful. Also, to be honest, more modern, let's say, than the original idea. Then, as a backend, we reuse something that was developed by our colleagues for neutrino underwater telescope, KM3net. This was designed originally to move data, stream data out of PMTs and at offshore Capo Passero is in Sicily, 50 kilometers away from the coast, and move all data to the onshore station where obviously, you can't do a trigger experiment at 4,000 meters down in the water, so you need to move data out and then use the CPU and whatever in onshore. So we use it, and obviously this requires some changes because it was meant for a different environment, a low rate, low signal rate experiment like neutrino detection, even if the background is huge and significant. This needed to be adapted to working in an accelerator condition, an experiment accelerator that is a little bit different. Anyway, we succeeded, and this was the backend we used to do our test. And then we use as the online reconstruction that is merged together with the TRIDAS. The JANA 2 this is a C++ framework where you can implement your sophisticated algorithm. For instance, in a specific case, we did our clustering to reconstruct the electromagnetic shower, or you can use also machine learning to do it in a more clever way, just to prove that in principle you have access to the entire package of software that easily is used offline. Then everything was controlled and coordinated by run control, used CBAF online data acquisition. That was just used, changed and organized to use also streaming readout. Normally at Jefferson Lab, all experiments are triggered, so this was something new. First validation, we used a prototype of the electron ion collider calorimeter. This is a lattice that just 9 channels placed behind one of the experimental hole. There is a photon beam with a tagger made mainly by a spectrometer, and then you have the energy of the photon hitting your calorimeter. So this was an external information, and this was fully assembled in the final configuration. And actually what we demonstrated in this simple configuration was that we were able to do a comparison one-to-one to the triggered acquisition and the streaming readout. The trigger acquisition had an FPGA programmed to check for the configuration where you have a seed with a lot of energy, the electromagnetic shower, and the other 8 crystals all around getting the remaining part. And so we demonstrated that preliminary test demonstrated that you can, at the end of the day, you can reconstruct the energy pretty well online, I mean, by software. And then we moved to a more, let's say, demanding or complicated configuration, not still, on the size of real experiment, but, in a little bit, the next step was to use the forward tagger in hole B. This is 332 Lhc calorimeter plus an odoscope, 224 scintillators, and a tracker, a micromegas tracker. It's about 3,000 channels. We just started with the calorimeter and the odoscope to demonstrate we were able to do local coincidence between plastic and crystals very fast, and in the streaming, within the streaming system. And we use a real reaction. This was a test on beam when the electron beam hit a lead target and aluminum target. And we used the PIsa inclusive photo production, or let's say quasi-real photo production, to identify 2 gammas within the calorimeter and the scattered electrons. The 2 gammas had the advantage that pi0 mass give you a kind of candle or a self-triggering reference, a self, let's say, analyzing reference. Actually, we spend a lot of time because you can imagine hydro production at very small angle is not trivial at all, even to make sensible prediction. To be sure that what we were measuring was actually what we were expecting. So we did a realistic simulation based on, on hydro production models that were quite sophisticated, and expecting about 2,000 events in 20-30 minutes of run from one target and about 400 from the other one. And actually, this is exactly what we measured at level of 10%. We were able to actually recover what we expected. Being able to reconstruct the cluster, all software, I mean, just streaming everything, and then software reconstructed the electromagnetic shower. Now, next step, since we demonstrated that we have a working system, this is not obviously the final system that we are going to use in the future, in particular for the Electron Collider, and we are thinking to a more clever way to assemble the different components that I just showed you before in what is called, this is a kind of framework based on microservices that talk each other with as little pieces of Lego. So you can replace whatever you like with your preferred, for instance, system for the back end, or you can replace the front end. And also the algorithms will be kind of transparent in the way that is going to be assembled together, and this will be the next step. And I think that this is going to be a very sufficiently general to be used also with an evolution of the software and hardware that we are expecting in the next 10 years, since the Electron Collider is not going to happen before 10 years from now. Last but not least, we also spent time in developing a giant-based Monte Carlo that intrinsically can stream data out. This seems to be trivial, but it is not, since giant is event-centric, while streaming intrinsically has time. And you have to feed it, you have to deal with that. I mean, define frames rather than events, where you have your data that spread over different time windows. And so we spend time, and we have a first prototype working, so we can really simulate data coming from the front end, either electronics or software. So in summary, I think that the streaming readout is the option for a future electron beam experiment. It actually is already, we are already testing for the present, not only for the future. And this is really taking advantage of the full detector's information for a smart triggering, filtering, whatever you want to do. There are so many advantages, performance, flexibility, scalability, upgrading, etc. But I think that what we need to do is demonstrate that it works at least as well as a trigger configuration. Obviously, we are convinced that it's going to work even better. But first of all, we need to convince ourselves and the rest of the community that it works as the trigger system. So we ran the first test in the Jefferson lab in 2 halls, hall D and hall B, in different configuration, and we have the full chain demonstrating that we have, the entire system that works. Now we are working to evolve it in a more general architecture, and obviously we can take advantage of the next years of being taking at Jefferson lab that will provide for free data and a test bench for the system, and also developing the Monte Carlo that obviously is important. And last but not least, the other thing, at least in the nuclear physics community where I'm coming from, may be different from HEP, we had also to work out let's say, the streaming readout community, because people were very skeptical in changing the trigger scheme to a streaming readout. I know LHCb and ALICE were, obviously they are doing a great job, and it's not really necessary to convince anybody that this is the solution. But in our case, we had also to work, within our own community to convince that this is a valuable option. Thank you very much for your attention.
Thank you for your nice presentation. We have time for a couple of quick questions.
In a triggered readout, once you get a trigger, you know that the data all belongs together. In a streaming readout, they come randomly in time, so you have to time tag each little bit of information with an absolute time, so that it's belongs together, and they have to be synchronized, and there should not be an overflow in the time count. So how do you address this problem?
So timing obviously is the base of streaming readout. As you mentioned, timestamp associated to the number, to the, say, digitized numbers, is the one that allows you offline, or let's say real time, to reconstruct from what is coming from, you have to reconstruct the time window where it happened. So the timing distribution is obviously critical. There are many different options. So far, I think that regenerating a signal, distributing a signal, and regenerating through PLLs, for instance, locally on the front-end electronics. Also, synchronization of different components over the network. We were thinking to using White Rabbit protocols, or something more sophisticated and standard, not deterministic network connection, because everything is expected. All this data flow needs to go more or less within a certain amount of time, where the CPU will be able to reconstruct the stream and rearrange in a time-ordered way. So this is obviously one of the issues that streaming readout needs to cope with.
Following up exactly the same thing. So if one of the subsystems is starting to fall behind for whatever fluctuating traffic reasons, do you then have a mechanism to drop data and catch up?
This is something that I don't think we study in details, but yes, there are general schemes where in principle you can recover. It's not even fully clear if you want to really stream the entire detector together, or you have to have some filter in between that kind of concentrators. Atlas had the Felix board, but we can think to a modern version of it that allows to have a partial aggregation of data, and then you can play with it, and then you can obviously control this aggregated flux and check that the big part of the stream is correctly streamed to the back end. There are different architectures. This obviously depends also on the size and the rate and the number of channels you have to deal with. So I think that the idea is to grow up and try to, to work with a solution that will be flexible enough to accommodate these issues. I mean, try to be sure that we can master it in real life. But what I show you was a real experiment, I mean, in an accelerator environment, so exactly the same condition as you have for trigger at the configuration. Obviously, 300 channels in place of maybe the 10 millions we are expecting from the electron-ion collider, so it's small scale, but demonstrating that we are on the right path, I guess.
Okay, there are no other questions. Let's thank the speaker again. This was the last talk of the session. Let's thank all the speakers of the session and also the poster presenters for the last time.
So, yeah, thank you very much, Rick and Martin. Now we have the other ICFA World Talk by Veljko Radeka, who should be connected on Zoom. Can we try to get Zoom? Hello, Veljko, can you hear us?
Yes.
Oh,
I'm
great.
here, so should just share the slides.
Yes, please.
Can you see me?
Yeah, we can see you.
Yeah.
Thank you very
here.
much for joining
Right.
us.
See? Yeah.
Does he have, shall I?
You now go to the.
You should be able to share your slides.
Yes. Great. Okay. Is the screen displayed?
No, we don't see the slides right now.
Yeah. Okay. Thank you very much. No.
Okay, now we see them. Maybe you can try to go full screen. Great, thanks a lot.
Okay. So I've been asked by the organizers to say something about the past developments and possibly the future. Now, looking at this title, a reasonable reaction would be all of us who have been working on advanced detectors have been practicing integral concept of sensors electronics. About past, we are not very much interested, and the future is difficult to predict. So what I've done here is to look at some breakthrough developments or ideas which took place some fairly long time ago, like 50, 60 years ago, which have continued to be used, developed, and are planned also for future detectors. Now, talking about the past, if you talk about the historical account by any participant, you will have to face that the history described by participant says history will be kind to us. I intend to write it. So this talk is not completely free from that. So looking at a limited selection of significant events in detector technology, I've selected only a few, and that was the germanium detector development started in 1963 and going very strong now. Next was the liquid argon ionization chambers, which have been obviously in use and also will be in the future. Next is the time projection chambers, the very important development in continuing use all these years and into the future. And then the development of liquid time projection chambers with both liquid argon xenon. In all of that, the important development of cryogenic electronics. I will mention only one development which illustrates how with relatively simple detectors in the early days of particle physics, some fairly great discoveries were made. So that was the spark chamber, which there hasn't been a single talk in any of the PIsa meetings, as far as I know, were used in the 50s, 60s, and led to 2 Nobel Prizes, one for the muon neutrino experiment, discovering of mu neutrinos, and also in CP violation experiment 64. So this is just to show how this type of detector had its very big role, not much future. So the first one is germanium detector, and in 63 came a real breakthrough that the Tavendale and Ewan at the Chalk River Laboratory in Canada made a small couple of cubic centimeters germanium detectors, PIN, and showed the spectrum at one meeting, which caused a revolution in nuclear spectroscopy, comparing to sodium iodide and getting what looked like a good resolution, much improved by an order of magnitude. Almost there was a flurry of activity on germanium detectors. So in 3 to 5 years later, the coaxial germanium detectors were made of sizes up to 100 cubic centimeters. And this shows you already the cold finger cryostats that are used with such detectors. Since germanium had to be operated at low temperature, it was also a start of cryogenic electronics by connecting JFET, junction field effect transistor, close to germanium. So that was a dramatic improvement, and those detectors then with the JFETs show the dramatic improvement compared to sodium iodide, achieved resolution which is very close to what is achieved today. With that, there was a development of low noise electronics, and for the energy resolution of 0.1% for germanium detectors developed in those years. And those techniques, early developments, were later used in many detectors, from solar neutrino detection, liquid argon calorimeters, later liquid TPCs, and these days further development in Agatha legend. Now, the very nice development has been made in large kilogram-sized detectors by rearranging the electrodes such that the charge is collected on a P+ contact, which is very small, on a very large detector. The point contact has a capacitance of 0.25 picofarad, and a wire bonded to a CMOS amplifier in this work reported in the NIM paper of a few years back. The noise achieved with this arrangement is down to about 5.6 electrons with very long processing integration time. And so there are many details in this development, which I cannot go into, but the main point is it is the close integration of CMOS and the point contact here that made possible to achieve such a low noise. So moving from that, in 1973 came the development of the first liquid argon sampling calorimeter, and more is known about that, so I won't go into great detail. But at that time, it demonstrated that that one can achieve very good resolution for electrons at that test beam of 7 GeV with this was the negative beam, this was with Cherenkov selected electrons. And the first measurements were made of charge collection in liquid argon and showing also the transit time, drift velocity in liquid argon. Now that development led to the Atlas calorimeter readout, which was done in really integral system design, where the calorimeter and the readout electronics were in a 1 Faraday cage, continuum connection, no gaps in the metal, which allowed then a very high resolution detector and very high stability and calibration. The Atlas calorimeter, this was also an innovation by Daniel Fournier, 1990, of accordion sampling, which is now the way for electromagnetic liquid argon calorimeters. So that Atlas calorimeter was one of the detectors in the Higgs discovery by Atlas and CMS, found at that time and announced in 2012, showing the data, what they look like, a small bump here, but with very good statistics, indicating it was the Higgs at about to around 126 GeV. The calibrations that this was that calorimeter has stability of response, a calibration of the order of less than 1.1%, so that provided more than 5 sigma confidence level in that experiment. The next came the breakthrough in '74, where David Nigre introduced gas time projection chamber. They are obviously one of the important tracking detectors in heavy ion colliders today, ALICE at LHC and at RIC. Showing a somewhat expanded view, not of this TPC, but of the general smaller CPC with 2 gem electrodes shown and pad electrode integrated closely with front-end ASICs. The challenges in dust detectors were positive ion space charge versus gain. One of the, I would say, continuing design issues. Going from that, we went the concept of liquid argon TPC was introduced by Herbert Chen, University of Washington, and Carlo Rubbia to use liquid argon, and which led to the development of Icarus, Microboon, Proto-Dune, eventually to Dune, which would be showing just an outline of a very large, more 10 kiloton active volume. Has to involve 60-meter long cryostat by 13 by 13 meter, just to illustrate what the one module would look with the cathode in the middle, vertical drift, the adult plane not shown. This, of course, is well known now that the ionization resulting from an interaction in liquid argon is then drifts to the sense wires and then the tracks are reconstructed. Just to illustrate, if you have several wire planes, a screen one and 3 sense wires where the electrons and feed lines go to collection, and the 2 induction plates, the ionization track drift here, and we end up with this kind of shape. Here, this was supposed to be, no. In connection with that, we came to, here is the, okay, it shows you how the track goes through induced signals causing bipolar induced current, and finally collection current on the collection plate. Along with that, then the cryogenic electronics, which started with JFETs, became obvious in around 2008 when microboom was started. The CMOS would be the best technology to use at low temperature. And this shows just the difference between the transconductance to drain current ratio at room temperature and in the cold for various channel lengths for NMOS and PMOS. So there is quite a bit of data crowded on this slide. Looking then proceeding with the designs, question was going from weak inversion, moderate inversion to strong inversion, where to do the design. It turned out that doing a low power design corresponding also to having devices where they would have very long lifetime, much longer than needed for experiments of 20, 30 years, more going extending to orders of magnitude higher. The much higher current densities or voltages were used for accelerated stress testing. An advantage for operation at low temperature was higher GM, higher speed, and lower noise. So going from that, show you the microboom experiment commissioned and started running in 2015. One that has produced most physics so far is first liquid argon TPC with cryogenic CMOS AC. Microboom had about 8,000 sense wires. The noise for all of these wires, which the induction planes had different wire lengths going to 5 meters. The collection plate had about 2.5 meter length constant. So this shows the noise, which was between 200 and 400 electrons after removal of any pickup noise. The signal-to-noise ratios are shown here, and whereas in the range of 20 to 40 with this type of cryogenic readout, which cannot be achieved with the warm external electronics outside of the cryostat. Going from that toward Dune to 2018, the prototype for the Dune electrodes and readout was completed with anode plane assembly with 6 meter long anode wires and long 7.5 meter long induction wires, called cryogenic electronics right on where the wires were terminated. With all the ASIC functions, which included ADC and digital processing. So it's called electronics module were attached directly to the wireframe, showing again quite high signal-to-noise ratio in the range of again, similar to micromoon, even somewhat improved at that time, showing one shower event and one muon here in the display in the protodune. So going from that, the developments proceeded toward the dune with the 3 ASIC design of a readout where the cold readout within connects to the warm interface within where the Faraday cage is completely completed with the crash-stand. The 3 ASIC design allows optimal choice of CMOS nodes, supply voltages to minimize power dissipation and large dynamic range. It was interesting to find that misspelled FPGAs were used in the protodune and also could successfully operate in at cryogenic temperatures. So going from this, if one looked at cold versus warm electronics, which used to be a, subject of very intense discussions, we see the real results, the two axes. One is the sense wire length. The other is if there is any cable between the sense wires electronics. So the only thing that we have in integral design is shown on this axis, noise increasing with the wire length, wire capacitance. If you start adding cable length for the external warm electronics, the noise increases and the cable lengths in a large crash start, such as in dune, would be just too long. And so essentially dune would not be feasible without cold electronics. So we stop and take a look at the times are changing, so are interests and activities. So most of the researchers and so today would be of this type, favoring computer analysis over building practical things. And one can see same in the children today. So what's the story then? There will be reliance on, in the research work in almost all areas of science, on artificial intelligence, machine learning methods will be dominant. In these results, you see papers relying on neural networks, deep learning, data healing algorithms, neuromorphic, autonomous experiments, and various exploration into the quantum effect-based systems. You can contrast to that the hardware, as I was showing with the germanium detectors, a 1/4 picofarad. So clearly most people would be active in the area in the left, and select few would be working on a hardware like that. Clearly, you would expect that those that work on physical aspects of detector sensitivity, low noise, so may find themselves in high demand. So that's the conclusion, and I thank you very much for the attention.
Thank you very much, Velko, for this fantastic, inspirational talk, and especially for the conclusion, which can be a very important signal for all the people here that are working on detectors and developments. Is there any comments or points that people want to make? I don't think we can ask questions, really, but maybe someone wants to make a comment? No? And then thank you very much again, and we'll deliver the plaque for the ICFA award to your address that I will request separately, and I think this is a great way of closing this conference. Thank you so much, Velko.
Thank you very much for this opportunity. I have fond memories of the PIsa meetings. I do remember well the person who organized Aldo Menzioni and the great meetings that were held at that time. Thank you again.
Thank you. So before we leave, I have a few final comments for the conference. If we can go back to the slides. So this has been very participated conference. Yes. This is many thanks, of course, are due. It was a very rich program, and many thanks to the conveners that helped us shape the program and participated actively and prepared the poster review talks, which was quite a daunting task given the huge number of posters. This is just a snapshot of the scientific program. We had overall almost 350 contributions between orals and posters and poster reviews. Many thanks to all the presenters, and I think the scientific quality was incredibly high throughout the conference. We also had a very rich industrial exhibit, 9 exhibitors, which I really thank for their support and sponsorship. We also had this industries roundtable, which was the first thing we tried, and I think it was a real success, so probably will continue. Just a quick look at the participation by region. We had a total of 400 participants. Clearly there's a large number from Italy, more than 200 just from Italy, and then 134 from Europe, but also we had quite a number from Americas, Asia, and Eurasia. And clearly these numbers here are smaller than in past editions, but that's due to the difficulty of traveling. We hope that in the next editions they will be overcome. If we then zoom in this area, excluding Italy, you can see here quite a few numbers from the United States, from Germany, from Switzerland, of course, from the UK, France, a good contingent from the United Arab Emirates, and then a good distribution across many, many countries, which is a very satisfactory picture of how this conference is interesting. Other numbers, age and gender balance, we had about 180 participants under 40 years old, which was a very refreshing view. There were a lot of young people, 80 students and many young postdocs, and we've seen many in the poster session, in the oral session. It was quite a pleasure. We had a reasonable female-male ratio, given the field. It was 20 to 80 in all categories, participants and posters and talks. slightly higher on conveners. We made a special effort to have a good gender balance, so we have 1/3 and 2/3. We assigned many awards during this conference. The ICFA Instrumentation Awards, which was the first edition. We had the 3rd edition of the Aldo Menzione Prize, and we had a regular Young Researcher Prize. Here, Frontier Detector for Frontier Physics is supporting all of these prizes. We also had the help from Kain and Hamamatsu in supporting the Young Researcher Prize. And here, some thanks to the selection committee, which was working very hard and very little time to select these young researchers. And these are some pictures of the various prizes, and we just heard the last talk by Velko. Some practicalities, these are needed. Buses will leave to the airports tomorrow at 7 from the hotels. Breakfast will start at 6:15 for those who need to catch the buses. From the Biodola area, so from this area, the buses are already tagged to Pisa or Rome, and they will start from the Hotel Hermitage, Hotel Biodola, and at the intersection of the Hotel Danila that now the people who stay at the Danila know very well. For the Procchio area, on the other hand, they will start as usual from the 3 hotels, Golfo, Perla del Golfo, and Desiree, but the buses are not necessarily tagged to Rome or Pisa because they don't match the number of participants. So some people will have to transfer the luggage on a different bus at the Portoferraio port. So there will be hostess to help you in that, but make sure you pay attention. Please check out of the hotel tonight, no later than 9 p.m., and don't try to check out tomorrow morning because that would be too hard. For participants who are not using the buses, then please leave your room tomorrow by 10:30, and so that the hotel can proceed. You can leave the luggage at the reception if you want. Now, finally, no work is done until the paperwork is done. So proceedings, they will be published in a special issue of Nuclear Instruments and Methods. We have very strict limits on the number of pages, and you can imagine that that's necessary given the number of contributions in this conference. There are instructions on the Indico side. The submission deadline is June 30, 2022. This will be fully refereed proceedings, so there will be regular papers at all effects. And now some thanks. So such a large conference is only possible thanks to the coordinated work of many people, and first and foremost the Frontier Detector for Frontier Physics Association, who is the motor and starting of all these conferences. Then the International Advisory Committee, the local organizing committee. Many thanks to the hotel and hotel staff. In terms of organization, the organization rests mostly on the INFN Pisa, which provides most of the support for the meeting, so many thanks to the director there. But also a lot of effort is done by INFN Bologna and CNAF with the multimedia group that has been sitting there for the entire conference and setting up all the video and the streaming and the Zoom connection and everything. This is also, there are recording of the conference on YouTube, so you can go back and see the talks again. So this is the picture from just an enlargement of the big manifest, and where you see the International Advisory Committee, the Organizing Committee. I just pointed out the name of Angelo Scribano, who's the president of the Frontier Detector for Frontier Physics Association, who's been one of the founder of the meeting and who's been, again, an engine in this process. And it's, I've been entrusted by the executive board with the chairmanship of this meeting, and Riccardo Pauletti has been entrusted with the deputy, and we've been very happy to do this, and I hope that the success of the meeting is a good recognition for all. Finally, some credit for the front line. These are the names of the people who you have seen around that maybe have been bussing you around or helping you at the secretary. And there are many other helping remotely, but I thought that giving the names of the people on site or directly connected here was a good recognition of their hard work. Thank you very much. Finally, many thanks to you, all participants, for coming to the meeting. I hope you enjoyed it. So have a safe trip home, but please consider that in 2 years from now, we will have the 16th PIsa meeting from May 26th to June 1st, 2024, and we hope to see you here. Normally, this meeting is on a 3-year. It is on a 3 years phase, but because of the pandemic, this is actually 21. You think you are in 22, but you're actually in 21. And so we are keeping the same phase. We agreed on this with Vienna and TIP, so that all the the various instrumentation conferences maintain the same phase, and they don't happen in the same year. So in this case, Vienna and PIsa meeting happen in the same year because of the pandemic postponement, but then it will come again in the regular phase. And so that's all. Have a safe trip back, and see you next time. Bye-bye.